Right now, as you lie perfectly still, you're racing through space faster than a bullet, 670 kilometers per hour, spinning 108,000 kilometers per hour, orbiting nearly 800,000 kilometers per hour, spiraling through the galaxy. Yet you feel nothing. Understanding this invisible motion reveals why ancient temples aligned with stars, why calendars collapse, why time itself bends, and why your very existence is a cosmic accident of perfect geometry. NASA's latest measurements confirm Earth's rotation is slowing by 1.7 milliseconds per century. The planet beneath you is literally losing time. Ancient coral fossils prove days were once only 22 hours long, but if we're always moving, never returning to the same point in space twice, where are we really going? Tonight we follow Earth's hidden choreography from the spin you cannot feel to the tilt that gives you seasons, from the orbit that bends time itself to the galactic current carrying our entire solar system toward an unknown destination. This isn't just astronomy, it's the story of how motion creates meaning, how ancient civilizations decoded these rhythms in stone, and how every breath you take is synchronized with forces beyond comprehension. By the end, you'll understand why Egyptian priests knew the equinox would arrive exactly 460 years in cycles, why the Maya calculated Venus's orbit to within minutes, and why modern physicists say that without Earth's 23.4-degree tilt, you wouldn't exist. Let's begin where all motion begins, with the illusion of stillness. Close your eyes. Feel the ground beneath you. Solid, unmoving, permanent. Now consider this in the time it takes you to draw a single breath. You've traveled more than 200 kilometers through space, not through any action of your own, but carried like a passenger on a ship so vast and smooth you cannot detect its motion. The Earth is not a platform. It's a carousel that has been spinning without pause for 4.5 billion years. Right now, if you're near the equator, the ground beneath you is rotating at 1670 kilometers per hour. That's faster than the speed of sound, faster than a bullet train, faster than most passenger jets. And yet your coffee sits perfectly still on the table. This is the great deception, the illusion that has fooled humanity for most of its existence. For thousands of years, humans looked up and saw the sun rise in the east arc across the sky and set in the west. The obvious conclusion seemed inescapable: the sun moves and we stand still. The ancient Greeks struggled with this paradox. If the earth truly spins, asked the philosopher Ptolemy, why don't we feel a constant wind? Why don't birds get left behind when they fly? Why doesn't everything slide off the surface? These seemed like reasonable objections. And so for nearly 1,500 years, the geocentric model Earth at the center, everything else revolving around us, dominated human thought. But a few minds glimpsed something deeper. Aristarchus of Samos, in the 3rd century BCE, proposed that Earth orbits the sun. He was ignored. Nearly 2 millennia later, Copernicus revived the idea, publishing his heliocentric model just before his death in 1543, perhaps fearing ridicule. Then came Galileo's elegant thought experiment. Imagine yourself below deck on a smoothly sailing ship, he wrote. Drop a ball and it falls straight down. Observe fish swimming in a tank, insects flying. Everything behaves exactly as it would on land. You cannot tell from inside the cabin whether the ship moves or rests at harbor. This is the principle of inertial reference frames, and it's the key to understanding why we feel nothing despite our tremendous velocity. Everything around you, the air, the ground, the oceans, even the atmosphere extending 100 kilometers above your head, moves together as one unified system. You're not moving through the air, you're moving with it. NASA's Jet Propulsion Laboratory has measured Earth's rotational velocity with extraordinary precision, using very long baseline interferometry, comparing signals from distant quasars billions of light-years away. The measurements confirm at the equator, the surface moves at 465 meters per second. At 45 degrees latitude, about 328 meters per second. At the poles 0, the axis itself, the point around which everything turns. But Earth's spin is only the first layer of motion. While the planet rotates once every 23 hours and 56 minutes, it simultaneously orbits the Sun at an average velocity of 29.78 kilometers per second. That's 107,000 kilometers per hour. In the time you've been listening, Earth has traveled roughly 3,000 kilometers along its orbital path. You're not where you were when this sentence began, and there's more. The Sun itself, carrying its entire family of planets, orbits the center of the Milky Way galaxy. Current measurements from the European Space Agency's Gaia mission show our solar system moving at approximately 220 kilometers per second relative to the galactic center, nearly 800,000 kilometers per hour. We complete one galactic orbit every 230 million years, a period sometimes called a cosmic year or galactic year. During Earth's last complete orbit around the galaxy, dinosaurs had not yet appeared. When we complete our next orbit, Earth may be unrecognizable. Layer these motions together, rotation, orbit, galactic motion, and you arrive at a stunning realization: you are traveling through space at nearly 1,000,000 kilometers per hour, and you have been since the moment you were born. Ancient cultures intuited this truth in ways we're only beginning to appreciate. The Sufi tradition includes the practice of whirling meditation, where dervishes spin in place for hours seeking to embody the rotation of the cosmos. The motion, they believed, connects them to the divine spinning of celestial spheres. Aboriginal Australians speak of the Earth as a living entity in constant motion, their Dreamtime stories describing the land itself as breathing and walking. The concept seems metaphorical until you consider what we now know: the Earth is indeed in constant motion, and we're walking on its surface as it journeys through space. Hindu cosmology describes the universe as an eternal dance. Shiva's cosmic dance of creation and destruction, the Nataraja. The symbolism depicts the universe in perpetual motion, never static, always becoming. Modern physics confirms this view. There is no such thing as absolute rest. Everything moves relative to something else. Even the atoms in your body are in motion. Electrons orbit nuclei at a significant fraction of the speed of light. The nucleus itself vibrates. At the quantum level, nothing is still. Motion isn't something happening to the universe. Motion is the universe. So why don't you feel any of this? The answer lies in acceleration, or rather the lack of it. Your nervous system evolved to detect changes in motion, not constant velocity. When a car accelerates or brakes, you feel pushed back or forward. When it cruises at steady highway speed, you feel nothing. Earth's motions, while tremendous in absolute terms, are nearly constant. The rotational speed varies only minutely. The orbital velocity changes slightly throughout the year, but smoothly, gradually. It's the same reason astronauts aboard the International Space Station feel weightless, despite traveling at 27,600 kilometers per hour. They're in free fall, constantly falling toward Earth, but moving fast enough sideways that they keep missing it. The sensation isn't zero gravity, it's zero acceleration. They and their spacecraft fall together. You experience a gentler version of this every moment. The ground, the air, your body all fall together in Earth's gravitational field while simultaneously moving through space. The result is perfect synchronization. No friction, no resistance, no sensation. Carl Sagan wrote that the Earth is a very small stage in a vast cosmic arena. He was right, but he might have added, it's a stage in furious motion, carrying its actors through the void at speeds that would terrify us if we could feel them. But here's where the mystery deepens. If everything moves together, if motion is only relative, then what does it even mean to say Earth is moving? Moving relative to what? The sun. The galaxy. Some absolute cosmic reference frame Einstein showed us. There is no privileged reference frame. No cosmic address that represents true stillness. Every point in the universe can claim to be at rest, with everything else moving around it. From the sun's perspective, Earth is indeed in motion. But from Earth's perspective, the sun moves across our sky. Both perspectives are equally valid. This leads to a profound philosophical question. If motion is only relative, if stillness and speed are interchangeable depending on your viewpoint, what does it mean to say anything is truly moving at all? Perhaps motion is less about displacement through space and more about relationship, how one thing changes position relative to another. In this view, the universe isn't a collection of objects moving through empty space. It's a web of relationships constantly shifting each object, defining the others through their mutual motion. The ancient Greek philosopher Heraclitus said, "No man ever steps in the same river twice, for it's not the same river, and he's not the same man." He might have gone further. You never occupy the same point in space twice, because the planet beneath you never stops moving. Tomorrow morning when you wake, you'll be millions of kilometers away from where you fell asleep, carried through the galaxy by forces so smooth and constant that your nervous system interprets them as perfect stillness. And this journey continues, has always continued, will always continue through night and day and the turning of years. The carousel never stops. You are, in the most literal sense, a traveler through the cosmos, whether you chose it or not. But motion alone doesn't fully describe Earth's journey, because while the planet spins and orbits and spirals through space, it also tracks time by a clock. Most of us never see the clock of the stars themselves. There's a clock that humanity forgot. It still runs perfectly precise, but most people will live their entire lives without knowing it exists. This clock doesn't measure time by the sun. It measures time by the stars, by Earth's true rotation relative to the distant cosmos. And here's the strange part. This hidden clock runs 4 minutes faster than the one on your wall. Every day you experience sunrise to sunrise, noon to noon, lasts 24 hours. We call this a solar day, but if you measure Earth's rotation against the background of stars instead of the sun, each complete spin takes only 23 hours. 56 minutes and 4 seconds. Astronomers call this a sidereal day, from the Latin word for star. 4 minutes doesn't sound like much, but those 4 minutes reshape the entire night sky. Here's why: while Earth spins on its axis, it's also moving along its orbit around the sun. Each day it travels about 2.6 million kilometers through space. By the time Earth completes one full 360-degree rotation, relative to the stars, the sun has shifted position slightly in the sky because we've moved along our orbital path. To bring the same spot on Earth back in line with the sun to return to noon, the planet must rotate a little bit more, about 1 degree extra. That extra rotation takes approximately 4 minutes. So the solar day, the one our entire civilization runs on, is actually slightly longer than Earth's true rotational period. We've been living by the sun's clock, not the planet's clock. This distinction might seem academic, but it has profound consequences. Because if you live by solar time, the stars shift position every single night. Each night, the same star rises about 4 minutes earlier than it did the previous night. Over a month, that's 2 hours. Over a year, those 4 minutes accumulate into a complete 24-hour cycle. This is why different constellations appear in different seasons. In July, Scorpius dominates the southern sky. By January, it's Orion. The stars haven't moved, you have. Earth's orbit around the sun means we face different directions in space throughout the year, and the sidereal clock tracks that change perfectly. Ancient astronomers understood this. They had to. Their survival depended on it. Consider the ancient Egyptians. They developed a calendar based on the heliacal rising of Sirius, the brightest star in the night sky. Each year, after being hidden by the sun's glare for about 70 days, Sirius would reappear on the eastern horizon just before dawn. This event, which occurred around mid-July, coincided with the annual flooding of the Nile, the most important agricultural event of the year. But here's what's remarkable. The Egyptians recognized that the solar calendar of 365 days gradually fell out of sync with the Sirius cycle. It took 460 years, what they called a Sothic cycle, for the two calendars to realign. This means they were tracking astronomical events across more than a millennium, passing knowledge from generation to generation with extraordinary precision. How did they calculate this without modern instruments? How did they even notice a drift that only becomes obvious after centuries of observation? The answer suggests something profound about how they viewed time itself. Egyptian civilization wasn't interested in short-term precision. They thought in terms of dynasties of cosmic cycles of eternal recurrence. Their monuments were built to last forever, aligned to stars that would guide them through eternity. The Great Pyramid's descending passage points to where Thuban in the constellation Draco would have been positioned as the pole star around 2500 BCE. As Earth's axis precesses slowly wobbling like a spinning top over a 26,000-year cycle, different stars occupy the position of the north celestial pole. To us, it's Polaris. To the pyramid builders, it was Thuban. This suggests they understood axial precession, a discovery officially credited to the Greek astronomer Hipparchus in 130 BCE. But if the pyramid's alignment is deliberate, it implies knowledge of precession more than 2,000 years earlier. The Maya achieved similar precision with their calendar systems. They used two interlocking cycles, the 365-day Hab solar year and the 260-day Tzolk'in sacred calendar. These cycles synchronized every 52 years in what they called a calendar round. But they also tracked something called the long count, which measured time from a mythical creation date in 3114 BCE. What's extraordinary is the Maya calculated the length of the solar year as 365.242 days. Modern measurements put it at 365.24289 days. They were accurate to within minutes without telescopes or atomic clocks. They achieved this through patient observation and something else, a different relationship with time. To the Maya, time wasn't linear. It was cyclical, layered, alive. Different calendars ran simultaneously, each measuring different types of time for different purposes. They didn't just track time, they inhabited it, moving through it the way we move through space. Hindu astronomy similarly demonstrates remarkable precision. The Vedic texts describe the nakshatra system dividing the ecliptic, the sun's apparent path through the sky, into 27 equal segments. Each nakshatra corresponds to a sidereal day, the time it takes for the moon to move roughly 13 degrees across the sky. These weren't arbitrary divisions. They reflect the actual motion of celestial bodies as seen from Earth's rotating surface. The texts include calculations for planetary positions that match modern astronomical data with stunning accuracy, suggesting centuries of careful observation. But here's the deeper mystery. All these cultures, Egyptian, Mayan, Hindu, Babylonian, developed sophisticated sidereal timekeeping independently. They recognize that the sun's clock and the stars' clock run at different rates. They understood that to track long cosmic cycles, you need to measure time by the unchanging stars, not the wandering sun. Today, professional astronomers still use sidereal time. When you visit a modern observatory, you'll often see two clocks on the wall, one showing local civil time, the other showing local sidereal time, LST. The sidereal clock tells astronomers which part of the sky is directly overhead at any given moment. Because stars rise 4 minutes earlier each night by solar time, but at exactly the same sidereal time. If a galaxy is at its highest point at midnight, LST tonight, it will be at its highest point at midnight LST tomorrow. And every night forever, as long as you measure by the stars, not the sun. NASA's Deep Space Network. The array of radio telescopes that communicates with distant spacecraft uses sidereal time for precise pointing. So does the Hubble Space Telescope, the James Webb Space Telescope, and every major observatory on Earth. They've returned to humanity's oldest clock, the rotation of Earth beneath the fixed stars. The European Southern Observatory's Very Large Telescope in Chile uses sidereal tracking systems accurate to a fraction of an arc-second. This allows it to keep celestial objects centered in view for hours, despite Earth's rotation. The technology is sophisticated, but the principle is ancient measure time by the stars, and the universe holds still. This raises a haunting question. If the sidereal day represents Earth's true rotational period, and the solar day is just a convenient fiction created by our orbit, which clock shows real time? From the universe's perspective, sidereal time is more fundamental. The stars provide the ultimate reference frame, distant, stable, unchanging on human timescales. They mark pure rotation, without the complication of orbital motion. But from a human perspective, solar time is what matters. We evolved under the sun's light, our circadian rhythms, our sleep cycles, our agriculture. Everything biological depends on the rising and setting of the sun, not the stars. So we inhabit two kinds of time simultaneously. Civil time, synchronized to the sun, governs daily life. Sidereal time, synchronized to the cosmos, governs the deeper rhythms of astronomy and navigation. Perhaps this is why ancient peoples built observatories like Stonehenge, the medicine wheels of North America, or the stone circles of Scotland. These weren't just temples. They were instruments, cosmic clocks that tracked both solar and sidereal time, marking solstices and equinoxes while simultaneously recording the rising of specific stars. Stonehenge's alignment to the summer solstice sunrise is famous. Less known is that from certain positions within the monument, specific stars appear through stone windows at predictable sidereal times. The structure functions as both a solar and stellar calendar, connecting human time to cosmic time. This suggests our ancestors didn't see these as separate. They understood intuitively what modern physics has proven, that time isn't a single river flowing independently. Time is a relationship between motion and observation, between the spinning Earth and the objects we watch move across the sky. When you look up tonight and see the stars in their positions, you're seeing them through Earth's sidereal clock. Tomorrow night, they'll have shifted slightly westward from the same solar time because the sidereal clock runs faster, 4 minutes faster every day, accumulating into the great wheel of seasons. The ancient astronomer priests knew this. They marked it in stone, tracked it across generations, embedded it in myth and monument. The Egyptian pyramid texts speak of the pharaoh's soul ascending to become a circumpolar star, one that never sets, that wheels eternally around the celestial pole. They chose immortality, measured by sidereal time, the time that never drifts, never fades. Perhaps they understood something we've forgotten in our rush through solar days, that there are different qualities of time, and the deepest truths are measured not by the sun's urgent cycle, but by the patient turning of Earth beneath eternal stars. The sidereal clock still runs, still measures, still marks each perfect rotation with precision our best atomic clocks confirm but cannot surpass. And as Earth spins beneath the stars, carrying you through another 23 hours, 56 minutes and 4 seconds of true rotation, the cosmos watches, keeping time by a clock older than civilization itself. But even as the stars track Earth's perfect rotations, another rhythm plays out, one the ancients also knew, though it defied easy explanation. The sun itself speeds up and slows down throughout the year, creating a puzzle that wouldn't be fully solved until Kepler stared at Mars through Tycho Brahe's impossibly precise observations. Stand outside at noon today, true solar noon, when the sun crosses directly overhead, your line of longitude. Tomorrow do the same. Use a precise clock, one synchronized to atomic time. You'll discover something strange. The sun won't arrive at exactly the same time. Depending on the date, solar noon might occur several seconds earlier or later than the day before. Over the course of a year, this variation accumulates to more than 16 minutes. The sun's apparent motion through the sky speeds up and slows down in a rhythm that repeats every 365 days. For millennia, this phenomenon baffled astronomers. If Earth's orbit were perfectly circular and its axis stood straight, the sun would behave like clockwork, rising and setting at predictable intervals with mathematical precision. But it doesn't. The reason is geometry, specifically the geometry Johannes Kepler discovered by obsessively analyzing Tycho Brahe's meticulous observations of Mars. Earth's orbit isn't a circle, it's an ellipse, a slightly flattened path that brings us closer to the sun at one point in our year and farther away at another. In early January, around January 3rd, Earth reaches perihelion, its closest approach to the Sun, about 147 million kilometers away.
6 months later, in early July, we reach aphelion, our farthest point, roughly 152 million kilometers distant. That's a difference of about 5 million kilometers, roughly 13 times the distance from Earth to the Moon. This matters because of Kepler's second law, sometimes called the law of equal areas. It states that a planet sweeps out equal areas in equal times as it orbits. Imagine drawing a line from the Sun to Earth. As Earth moves along its orbit, that line traces out a wedge-shaped area. Kepler discovered that these areas are always equal over equal periods, whether Earth is near the Sun or far from it. But here's the crucial insight to sweep equal areas. When you're closer to the Sun, you must move faster. When you're farther from the Sun, you move slower. The geometry demands it. At perihelion, Earth's orbital velocity reaches about 30.3 kilometers per second. At aphelion, it slows to approximately 29.
3 kilometers per second, a difference of 1 full kilometer per second, or 3,600 kilometers per hour. This change in speed has a direct effect on how the Sun appears to move across the sky. When Earth is moving faster in its orbit, it must rotate slightly more to bring the Sun back to the same position overhead, making solar days slightly longer. When Earth moves more slowly, solar days are slightly shorter. But there's a second factor complicating things: Earth's axial tilt. The planet's axis tilts 23.4 degrees relative to the plane of its orbit. This tilt means the Sun's apparent path across the sky, called the ecliptic, is angled relative to the celestial equator. As a result, the Sun's east-west motion varies throughout the year. Sometimes it moves more directly along the equator, other times it moves diagonally following the ecliptic's angle. These two effects, Earth's elliptical orbit and its axial tilt, combine to create what astronomers call the equation of time. The difference between apparent solar time, what a sundial shows, and mean solar time, what your clock shows. If you plot this difference throughout the year, it creates a beautiful curve. In early November, the Sun runs about 16 minutes behind clock time solar. Noon occurs 16 minutes after 12:00 p.m. In mid-February, the Sun runs about 14 minutes ahead, 4 times a year. Around April 15th, June 14th, September 1st, and December 25th, solar time and clock time align perfectly. Ancient navigators knew this instinctively, even without understanding the mathematics behind it. Polynesian wayfinders who crossed thousands of miles of open ocean using only stars and wave patterns recognized that the Sun's position at a given time shifted throughout the year. They incorporated this knowledge into their navigation, treating the Sun as a less reliable timekeeper than stars. The ancient Babylonians documented these variations in astronomical diaries, recording the time between sunrise and sunset with remarkable precision. They noticed the discrepancies but lacked the theoretical framework to explain them. It would take Kepler nearly 2 millennia later to unlock the geometric truth. When Kepler published his laws of planetary motion in the early 1600s, he provided the first mathematical proof that orbits are elliptical, not circular, a revolutionary idea that shattered the aesthetic preference for perfect circles that had dominated astronomy since Plato. But proving elliptical orbits wasn't enough.
Kepler needed to explain why. That answer came from Isaac Newton, who showed that gravity and inverse square force, decreasing with distance, naturally produces elliptical orbits. The sun pulls harder when Earth is closer, accelerating our motion. It pulls more weakly when we're farther, allowing us to slow down.
This has a counterintuitive consequence. Earth moves fastest in its orbit during northern hemisphere winter, when the sun's intensity feels weakest. The reason is the tilt, not the distance. The northern hemisphere tilts away from the sun in winter, making sunlight strike at a shallow angle despite Earth's proximity. Distance changes the sun's brightness by only about 3%, far less than the effect of axial tilt. The ancient Greeks worried about this discrepancy. If the seasons were caused by Earth's distance from the sun, they reasoned, shouldn't winter and summer occur simultaneously across the globe? The fact that seasons reversed between hemispheres troubled them. The Maya resolved this through observation. They tracked the sun's path across the sky throughout the year, noting that it climbed higher in summer and lower in winter, not brighter or dimmer, but higher or lower. This suggested the angle of sunlight mattered more than distance, a conclusion modern physics confirms. Temperature depends on solar energy per unit area, which is determined primarily by the angle of incidence, not distance. The equation of time has practical consequences beyond philosophy. Before the invention of accurate mechanical clocks, sundials were the primary timekeeping devices. But a sundial shows apparent solar time, which drifts relative to mean solar time throughout the year. To convert sundial time to clock time, you need to apply a correction, the equation of time. Clockmakers in the 17th and 18th centuries began inscribing equation of timetables directly onto clock faces, allowing users to adjust readings based on the date. Some elaborate clocks included mechanical cams shaped to apply the correction automatically, tiny analog computers compensating for the eccentricity of Earth's orbit. This became critical for navigation. In the 18th century, determining longitude at sea required comparing local solar noon to Greenwich Mean Time. Navigators used marine chronometers, highly accurate clocks set to Greenwich time. By observing when the sun reached its highest point locally and comparing that to the chronometer, they could calculate their east-west position. But this only worked if they accounted for the equation of time. A navigator who forgot to apply the correction might calculate their longitude incorrectly by hundreds of kilometers, potentially fatal in unfamiliar waters. John Harrison's famous chronometers, developed in the mid-1700s, revolutionized navigation by maintaining accuracy to within 1 second per day, precise enough that the equation of time became the limiting factor rather than clock drift. Suddenly, astronomical knowledge became as important as timekeeping technology. Today, this same principle governs GPS satellites. Each satellite broadcasts timing signals referenced to atomic clocks. Receivers on Earth calculate position by comparing signals from multiple satellites. But the system must account for relativity effects, Earth's rotation, orbital mechanics, and yes, the equation of time. Without these corrections, GPS would drift by more than 10 kilometers per day. The elliptical orbit that puzzled ancient astronomers now shapes the technology in your phone. If you want to see the equation of time visualized, look at a globe. Many globes include a figure-8 shape somewhere in the Pacific Ocean. This is called the analemma, the path the sun traces in the sky if photographed from the same location at the same clock time every day for a year. The analemma's shape results from the combination of Earth's elliptical orbit and axial tilt. The north-south extent reflects the tilt the sun reaches its highest point at summer solstice and lowest at winter solstice, a range of 47 degrees. The east-west width reflects the equation of time, the sun's apparent motion speeds and slows, causing it to drift east and west by about 16 minutes total. This figure 8 is a signature of imperfection, proof that Earth's motion is elegant but not simple, governed by gravity's precise mathematics, but expressed through geometry's subtle variations. Ancient astronomers documented these patterns without understanding their cause. The Babylonians recorded the lengths of daylight throughout the year with meticulous care. Indian astronomers calculated the tithi, a lunar day that accounts for both moon's motion and Earth's variable orbital speed. Chinese astronomers noted that solar and sidereal time diverged in predictable cycles. They treated these as empirical facts observations to be recorded and predicted without the theoretical framework to explain them. Yet their predictions were often remarkably accurate, suggesting that mathematical pattern recognition can proceed independently of physical understanding. Perhaps this is why ancient astronomy is often blended with astrology and mysticism. Without causal mechanisms, celestial patterns seemed like messages rather than mechanics, the universe speaking in symbols that must be interpreted rather than equations that must be solved. Today we've reversed this relationship. We understand the causes, but perhaps lost some capacity for wonder. When NASA's Solar Dynamics Observatory captures the sun in wavelengths invisible to human eyes, revealing magnetic field lines and plasma dynamics, we see mechanism. Ancient observers, watching the same sun trace its analemma across the sky, saw mystery. Which perspective is richer? The modern view provides power prediction navigation technology. The ancient view provided meaning connection to cosmos ritual aligned with celestial rhythm time experienced as sacred rather than measured. Perhaps both are necessary. The equation of time is a mathematical correction factor, yes, but it's also a reminder that nature doesn't conform to human preference for simplicity. The universe is precisely lawful but never simplistic. Earth's orbit is perfect for sustaining life, but imperfect in its geometry, fast and slow elliptical rather than circular. And this imperfection, this variation creates the rhythm of seasons and the shifting sky, the very patterns that make Earth dynamic rather than static, changing rather than eternal. As you sleep tonight, Earth continues its elliptical journey, accelerating imperceptibly toward its January rendezvous with the sun or decelerating toward its July distance. The sun's apparent motion through your sky speeds or slows by seconds you'll never notice. Yet over months, the equation of time reshapes when sunrise occurs, when day becomes night, when one season transforms into another. The ancient Egyptians called this Ma'at cosmic order, emerging from complexity harmony, arising from variation. They weren't wrong. The equation of time is chaos, becoming pattern motion, becoming music. But there's an even deeper question lurking beneath these orbital mechanics. Does time itself exist, or is it merely a measure of motion? And if Earth stopped moving, would time stop too? Imagine two twins. One remains on Earth. The other boards a spacecraft and travels near the speed of light to a distant star and returns. When they reunite, the traveling twin has aged less, perhaps years less, or even decades, depending on the journey. This isn't science fiction. This is relativity. And it reveals the most shocking truth about time: it doesn't flow uniformly throughout the universe. Time is relative, flexible, and profoundly strange. For thousands of years, humanity operated under a comforting assumption: time is absolute. Clocks might be more or less accurate, but time itself was thought to flow everywhere at the same rate, an independent river carrying all events forward in lockstep. A second on Earth equaled a second on the Moon, on Mars, in distant galaxies. Time was the one universal constant. Then Albert Einstein shattered this certainty. In 1905, Einstein published his theory of special relativity, demonstrating that time and space are not separate entities, but aspects of a unified structure called space-time. More importantly, he proved that time's flow depends on motion. The faster you move, the slower your clock runs, not because your clock malfunctions, but because time itself dilates. The mathematics are precise. An observer moving at velocity v experiences time at a rate given by the Lorentz factor. Time appears to slow by a factor dependent on the ratio of velocity to light speed. At everyday speeds, this effect is negligible, but approach the speed of light and time slows dramatically. At 90% of light speed, time runs at about half its normal rate. At 99.9%, time slows to about 4% of its stationary rate. This has been tested exhaustively. In 1971, physicists Joseph Haffel and Richard Keating placed cesium atomic clocks aboard commercial airliners and flew them around the world, both eastward and westward. When compared to identical clocks that remained on the ground, the flying clocks showed measurable differences a few hundred nanoseconds, exactly matching Einstein's predictions. Eastward flying clocks lost time relative to ground clocks. Westward flying clocks gained time. Why the difference? Because Earth rotates eastward. Flying east means moving faster relative to Earth's center, while flying west means moving slower. The additional velocity affects time's flow. These aren't hypothetical effects. They govern the technology you use daily. GPS satellites orbit Earth at about 14,000 kilometers per hour. At this velocity, time aboard the satellites runs slower than time on Earth's surface, but only by about 7 microseconds per day due to their motion. However, there's a counteracting effect. The satellites are also in weaker gravity, and Einstein's general relativity predicts that time runs faster in weaker gravitational fields. This effect dominates, causing satellite clocks to run about 45 microseconds per day faster than ground clocks. The net result, without relativistic corrections, GPS positions would drift by about 10 kilometers per day. Every location calculation you receive, every navigation instruction, every tracked delivery depends on compensating for the fact that time flows differently in space than on Earth. General relativity extends this insight further. Einstein showed that mass warps space-time, creating what we experience as gravity. The stronger the gravitational field, the slower time flows. Near a massive object, clocks tick more slowly than they would in empty space. This has been confirmed repeatedly. Atomic clocks at different altitudes run at different rates, measurable even for height differences of just 1 meter. Your head ages slightly faster than your feet because it's farther from Earth's center and experiences fractionally weaker gravity. The difference is absurdly small, a few hundred attoseconds per day, but real and measurable with modern optical lattice clocks. Near a black hole, time dilation becomes extreme. At the event horizon, the point of no return time appears to stop entirely from an outside observer's perspective. An astronaut falling into a black hole would experience time normally, but to someone watching from a safe distance, the astronaut would appear to freeze, never quite crossing the horizon, their image red-shifting and dimming, but never disappearing. This isn't perception or illusion. Time genuinely flows at different rates in different gravitational fields. There is no universal clock ticking the same seconds throughout the cosmos. Every point in space experiences its own time, its own now, based on its velocity and local gravitational potential. This realization dismantles our intuitive understanding of simultaneity. Two events that occur at the same time, according to one observer, may occur at different times according to another observer moving at a different velocity. There is no absolute now shared across the universe. The present moment is local, not universal. Ancient philosophies sometimes intuited this truth. Buddhist teachings speak of dependent origination, the idea that no phenomenon exists independently, but only in relation to other phenomena. Applied to time, this suggests that moments don't exist in isolation, but only in relation to observations and events. In Sanskrit, the concept of kshana, an instant or moment, is described as infinitely divisible with no smallest unit of time. Time emerges from process rather than existing as an absolute background.
Hindu cosmology describes time as Kala, but also speaks of Brahman existing beyond time in a state where past, present, and future are simultaneous. Modern physics offers a parallel the block universe interpretation of relativity, where all moments past, present, future exist equally in four-dimensional spacetime.
The flow of time is an illusion of consciousness, not a feature of reality itself. This raises profound questions. If time's rate depends on motion and gravity, what is time? Fundamentally, modern physics suggests time isn't a thing unto itself, but a dimension of space-time, a coordinate that marks change and causation but doesn't exist independently of events. The physicist John Wheeler summarized it elegantly: time is nature's way of keeping everything from happening at once. It's a bookkeeping system, a way of ordering events into before and after. But the rate of that bookkeeping varies, depending on your reference frame. Consider the James Webb Space Telescope orbiting the Sun at the L2 Lagrange point about 1.5 million kilometers from Earth. Time flows differently there than on Earth's surface, faster because it's farther from our planet's gravity, but the effect is minuscule. Yet when JWST observes distant galaxies, it's literally looking backward in time. The light from a galaxy 13 billion light-years away left that galaxy 13 billion years ago. We're seeing the galaxy as it was in the ancient past, not as it exists now. In fact, there is no now for that galaxy from our perspective. The concept of simultaneity breaks down across cosmic distances. By the time we observe the galaxy's light, it may no longer exist. Or it might have evolved into something unrecognizable. We'll never know what's happening now in that galaxy because information can't travel faster than light. This leads to an unsettling conclusion: the universe doesn't have a synchronized timeline. Every observer, every reference frame experiences their own unique sequence of moments. We're all traveling through space-time along different trajectories, and those trajectories never perfectly align. Ancient navigators understood time through observation of cycles, lunar phases, seasonal changes, stellar rising and settings. These cycles provided meaning and order, but they also recognized time's multiplicity. The sacred calendar might disagree with the solar calendar, which disagreed with the lunar calendar. Rather than seeing this as confusion, many cultures accepted multiple concurrent times, each valid for different purposes. The Maya had at least 17 different calendars, running simultaneously, tracking everything from Venus's synodic period to the pregnancies of gods. Time wasn't singular, it was layered, cyclical, multidimensional. Perhaps they understood something we're rediscovering through relativity: time is plural, not singular. There are many times, each defined by different frameworks and relationships. Einstein's equations don't just predict time dilation, they forbid universal simultaneity. The mathematics are unambiguous. If you accelerate away from me at high speed, then decelerate and return, less time will have passed for you than for me, not because of trickery, but because you and I literally moved through time at different rates. This is now routine. Muon's subatomic particles created in Earth's upper atmosphere have a lifetime of about 2.2 microseconds in their own reference frame. They're created 10 kilometers above Earth's surface by cosmic ray collisions. At near light speed, they should decay long before reaching the ground. But they don't. We detect them in abundance at sea level because from our perspective their clocks run slow. Time dilation extends their lifespan. From the muon's perspective, however, something different happens. In their frame, time runs normally, but the distance to Earth's surface contracts due to length contraction, another relativistic effect. Either explanation gives the same result: the muons reach the ground. This illustrates a profound insight: different observers can use different explanations for the same phenomenon, and both will be correct. Reality isn't a single narrative. It's a multitude of perspectives that quantum mechanics and relativity somehow reconcile into consistent experience. If all this sounds impossibly strange, it's because evolution didn't prepare us for relativistic speeds or gravitational extremes. Our intuitions developed in an environment where Newtonian physics is an excellent approximation. We never needed to understand time dilation to survive as hunter-gatherers. But the universe doesn't care about human intuition. The mathematics and experiments are clear. Time is not universal. It bends, stretches, and slows depending on how you move through space and how deep you sit in gravity's well. This has implications for existence itself. If time doesn't flow uniformly, then when are you? The question sounds absurd until you recognize that your now isn't the same as a GPS satellite's now or a distant star's now. You occupy a specific moment in your reference frame, but that moment isn't shared universally. The ancient Greeks debated whether time existed outside of change. Aristotle argued that time is the measure of motion. Without motion, there would be no time. Modern physics supports a version of this view. If every particle in the universe stopped moving, every quantum fluctuation froze, the equations suggest time would become meaningless. Time exists because things change, not the other way around. So when you ask, does true time exist? The answer is both yes and no. Time exists as a dimension of space-time as real as length or width. But universal absolute time flowing everywhere at the same rate does not exist. Time is local relative and observer dependent. Tomorrow, when you glance at your clock and trust that it shows the time, remember it shows your time. Earth's time as experienced in our particular reference frame at our particular gravitational potential. An astronaut aboard the International Space Station experiences a different time. A satellite in higher orbit experiences yet another, and a photon racing through space experiences no time at all from its perspective. It's emitted and absorbed in the same instant regardless of how far it travels. We are all time travelers, moving through space-time at different rates, our clocks diverging imperceptibly but inexorably. And this revelation, perhaps more than any other, reveals how profoundly strange the universe truly is, how the familiar rhythms of sunrise and sunset of clocks and calendars are local phenomena in a cosmos that keeps no universal time. But if time bends and shifts with motion, then even something as simple as noon, the midpoint of day, can't occur at the same moment everywhere. And that realization changed human civilization forever. When is noon? The obvious answer seems clear: 12:00 p.m. But step outside at that moment with a sundial, and in most places the sun won't be directly overhead. In fact, for the majority of Earth's surface, solar noon, the moment when the sun reaches its highest point, rarely coincides with clock noon. This discrepancy isn't an error. It's the inevitable consequence of imposing a grid of human time zones onto a spherical planet that rotates beneath the sun. Before the late 19th century, every town kept its own local time based on solar position. Noon meant the moment when the sun crossed the meridian, the imaginary line running from north to south through the sky directly overhead. Each town's noon occurred at a slightly different moment than its neighbors. This worked fine in an era of slow travel. If you lived your entire life within a few kilometers, the fact that the neighboring village's noon occurred 4 minutes before yours mattered not at all. But then came the railroads. Trains connected distant cities operating on published schedules. A train leaving Boston at noon and arriving in New York 4 hours later seemed simple enough, except noon in Boston and noon in New York were different moments. Boston's solar noon occurred about 12 minutes before New York's because Boston is farther east. Railway companies attempted various solutions. Some used the local time of their headquarters city for all stations. Others tried to split the difference, creating compromise times that satisfied no one. The result was chaos. A single railway station might have 3 or 4 clocks showing different times, depending on which company's trains departed from which platform. On November 18, 1883, American railroads imposed a solution. They divided the continent into 4 time zones and synchronized all clocks within each zone. Towns protested, insisting on their God-given solar time, but practicality won. Within a year, most of the nation had adopted standardized time. The International Meridian Conference of 1884, held in Washington, D.C., extended this system globally. Delegates from 25 nations agreed to divide Earth into 24 time zones, each spanning 15 degrees of longitude. They selected the Greenwich Observatory in England as the prime meridian zero longitude, in part because much of the world's shipping already used British nautical charts. From Greenwich time zones extended eastward and westward, each 1 hour apart. In theory, this meant that solar noon should occur close to clock noon in the middle of each time zone with variations of up to 30 minutes at the zone's edges. But theory and practice diverged immediately. Time zones became subject to political boundaries, geographical considerations, and national pride. Spain, which geographically sits west of the Greenwich Meridian, adopted Central European time, placing it an hour ahead of where solar time suggests it should be, a remnant of Franco's decision during World War II to align with Nazi Germany, never reversed. China, spanning 5 theoretical time zones, uses only one Beijing time. This means that in Xinjiang province, in China's far west, solar noon occurs around 200 p.m. clock time. Residents adapt by shifting daily rhythms, but the disconnect between sun and clock remains. Even the United States has oddities. Alaska uses its own time zone, but the Aleutian Islands stretch so far west that one island, Attu, lies east of New Zealand on the globe. India uses a half-hour offset, placing it at UTC plus 5:30. Nepal uses UTC plus 5:45, a quarter-hour offset unique in the world. These political decisions sever the connection between time as shown on clocks and time as experienced by the sun. For most of human history, time was local, immediate, anchored to the visible sky. Now time is global, synchronized, and often disconnected from celestial reality. This has biological consequences. Human circadian rhythms evolved to synchronize with the sun's cycle, using light exposure to regulate melatonin production, body temperature, and sleep-wake patterns. When clock time diverges significantly from solar time, our internal clocks struggle to adjust. Studies of sleep patterns across time zones reveal measurable differences. People living on the eastern edge of a time zone where the sun rises and sets earlier relative to clock time tend to wake earlier and align better with conventional schedules. Those on the western edge where sunrise occurs later show increased rates of sleep deprivation and circadian misalignment. Spain's late solar noon contributes to its famous culture of late dining and late bedtimes. Spaniards aren't inherently night owls. They're compensating for a clock that's out of sync with their sky. Similarly, workers in Western China face chronic jet lag despite never crossing a border. Their clocks say it's time for work, but their biology knows, the sun says otherwise. Ancient timekeeping avoided this problem by remaining local. Islamic prayer times calculated based on solar position still vary by location, with mosques determining prayer times based on when the sun reaches specific angles above or below the horizon. These times shift naturally with the seasons, and longitude remaining forever aligned with the sun's actual motion. Jewish halakhic hours divide the period from sunrise to sunset into 12 equal parts, meaning an hour is longer in summer than winter. This ancient system, still used for religious observances, treats time as dynamic rather than fixed, a reflection of lived experience rather than mechanical regularity. The disconnect between solar and civil time also affects agriculture, though less so in the modern era of artificial lighting and climate control. Traditional farming, however, followed the sun. Cows don't produce milk on schedule to human clocks. They respond to dawn and dusk. Chickens lay eggs according to photoperiod, not wristwatches. In regions near the edges of time zones, farmers sometimes ignore clock time entirely, conducting operations according to solar position. This creates a shadow timekeeping system running parallel to official time, acknowledging a truth the clock denies. The sun doesn't care about political boundaries. There's a deeper question lurking here. What is the purpose of time? If time exists to coordinate human activity, then standardized time zones succeed brilliantly. If time exists to align human life with natural cycles, then time zones fail profoundly. Ancient peoples didn't face this dilemma because they lacked the technology to synchronize distant locations. Time was inherently local. The sun rose when it rose, set when it set, and that was that. The question of what time it was 1,000 kilometers away would have seemed meaningless, like asking what color the sky is on the other side of the world. It's whatever color it appears to be there. You're not there, so why would you need to know modernity demands synchronized time for coordination of global activities, communication, commerce, travel? But this convenience comes at the cost of divorcing time from place. When it's noon in New York, it's also noon in Miami, despite the sun being in different positions in the sky. The word noon no longer primarily means sun at its highest, but rather the moment clocks say 1200. We've redefined time from an astronomical phenomenon to a social construct. This isn't necessarily wrong, but it is a fundamental shift in how humanity relates to the cosmos. For 200,000 years, our ancestors lived by the sun. Only in the last 140 years have we lived by the clock. Evolutionarily speaking, we're still sun timers forced to operate in clock time. There's a haunting beauty in this. Stand at the edge of a time zone, right at the stroke of noon. On one side of an invisible line, watches say 1200 p.m. Step across and they say 100 p.m. But the sun doesn't care. It's in the same position, casting the same light, maintaining its patient arc across the sky. The sun keeps solar time indifferent to our grids and boundaries. If you want to experience true noon solar noon, you need to calculate it. Determine your exact longitude. Apply the equation of time to correct for Earth's elliptical orbit. Adjust for daylight saving time if applicable. Only then can you step outside at the precise moment when the sun crosses your meridian, when shadows point true north, when you're aligned with the ancient rhythm. Most people never do this. Most people will live their entire lives without experiencing true solar noon even once. We've accepted clock noon as a convenient fiction, just as we've accepted so many other approximations that make modern life function smoothly, but disconnect us from direct experience. Perhaps this is the price of globalization, of being able to schedule a phone call with someone on the other side of the world, of trains that run on time, of GPS satellites that need synchronized clocks to function. We gain coordination at the expense of cosmic connection. But the sun doesn't forget. Every day at your precise location, solar noon occurs. The moment is brief, unremarked, unnoticed. The sun reaches its highest point, begins its descent, and continues its eternal journey across your sky. Whether you acknowledge it or not, that moment exists a link to the billions of solar noons that came before and the billions yet to come. Ancient peoples marked solar noon with monuments. The Jantar-Mantar observatories in India include enormous sundials accurate to within seconds. Stonehenge's alignment captures solstice sunrise with precision. The Temple of Karnak in Egypt has a light box that illuminates the Holy of Holies only at winter solstice dawn. These structures say this moment matters. The sun's position matters. Alignment with cosmic motion matters. We've built a civilization that largely ignores these moments, yet they continue. Every day, solar noon sweeps across the planet like an invisible wave traveling westward at 1,670 kilometers per hour at the equator, the speed of Earth's rotation. If you could see this wave, you'd watch it move from Japan to China to India to Arabia to Europe to the Atlantic to the Americas, circling the globe every 24 hours, an eternal tide of maximum sunlight. You are part of that tide whether you know it or not. Your cells respond to it. Your rhythms follow it. Your biology tracks it even when your consciousness does not. The ancient part of your brain, the hypothalamus, the suprachiasmatic nucleus, measures light and dark, estimating solar position throughout the day. You're a walking sundial. your internal clock trying to stay synchronized with the sun even as your wristwatch tells a different story. As you rest tonight, consider setting an alarm not for 700 a.m. clock time, but for sunrise. Not for noon, but for solar noon. Experience just once the moment the ancient peoples knew so well, the moment when you and the sun align, when your meridian and the sun's position meet. When for one instant you stand at the center of your own sky. It won't match your clock, but it will match the cosmos. And perhaps in that moment you'll feel what we've nearly forgotten, that we are not separate from the sun's journey, but part of it, turning beneath it, carried along in its light, dancing to a rhythm far older than clocks or time zones or any human measure of hours and minutes. The sun keeps perfect time. It's humanity that invented the concept of being late. But here's an even more unsettling revelation. Earth isn't just spinning beneath the sun and tracking time by stars and seasons. It's also moving through the galaxy, hurtling toward a distant gravitational anomaly we can barely see, pulled by forces we still don't fully understand. There's a question we rarely ask, perhaps because the answer is so profoundly unsettling. Where is Earth going? Not where is it going in its orbit around the sun, that's straightforward, predictable. A simple ellipse we understand completely, but where is the Earth going in the larger sense, as part of a solar system that orbits the galaxy, as part of a galaxy that moves through intergalactic space? The answer is, we're being pulled towards something we can't quite see, something so massive that it's dragging our entire galaxy and hundreds of thousands of neighboring galaxies toward it at 2.1 million kilometers per hour. Astronomers call it the Great Attractor, and it's one of the most mysterious structures in the observable universe. Let's start with what we know. The Sun, carrying all its planets, including Earth, orbits the center of the Milky Way galaxy. This orbit takes approximately 230 million years to complete a period called a galactic year. During the last complete galactic year, dinosaurs hadn't yet appeared on Earth. When we finish the current galactic year, Earth may be unrecognizable. The European Space Agency's Gaia spacecraft has mapped the motion of over 1.5 billion stars within the Milky Way, revealing the precise choreography of galactic rotation. The Sun sits about 26,000 light-years from the galactic center, moving at approximately 220 kilometers per second, nearly 800,000 kilometers per hour. At this velocity and the time it takes you to sleep for 8 hours, the solar system travels more than 6 million kilometers through the galaxy. You never return to the same point in space. Every moment of your life exists at a unique galactic coordinate that will never be revisited. But this orbital motion is only part of the story. The Milky Way itself is moving and moving in a very specific direction. In the 1970s, astronomers noticed something peculiar about the cosmic microwave background CMB, the faint glow of radiation left over from the Big Bang. The CMB should appear uniform across the sky, but instead it shows a dipole pattern, slightly warmer in one direction, slightly cooler in the opposite direction. This dipole doesn't result from actual temperature variations in the early universe. It's a Doppler effect caused by our motion relative to the CMB's reference frame. We're moving toward the warmer region, blue shifting the radiation, and away from the cooler region, red shifting it. By analyzing this Doppler shift, astronomers calculated that the Milky Way is moving at approximately 600 kilometers per second relative to the CMB rest frame, more than 2 million kilometers per hour. We're heading toward a region of space roughly in the direction of the constellations Hydra and Centaurus. What's pulling us? The initial answer was the Great Attractor, discovered in the 1980s through observations of galaxy motions. By measuring the redshifts of hundreds of galaxies and comparing them to their expected motion due to cosmic expansion, astronomers found a large-scale deviation. Galaxies in our region of the universe aren't just moving apart due to expansion, they're also flowing toward a common point. That point lies about 150 million light-years away, hidden behind the zone of avoidance, a region of space obscured by the Milky Way's own dust and gas. This makes direct observation difficult, but gravitational effects are unmistakable. Something massive sits there, pulling on everything around it. Further observations revealed an even larger structure, the Laniakea supercluster, a collection of over 100,000 galaxies spanning 520 million light-years. Our Milky Way is just one galaxy within this vast structure, all flowing along gravitational streamlines toward regions of higher density. But Laniakea itself is being pulled. Beyond it lies the Shapley supercluster, an even more massive concentration of galaxies exerting gravitational influence across cosmic distances. The flow doesn't stop. It's a hierarchy of motion. Earth orbits the Sun orbits the galactic center. The galaxy flows through the local group falls toward the Great Attractor. The Great Attractor flows toward Shapley, and Shapley itself may be drawn toward structures beyond our current observational capacity. We're passengers on a ship navigating currents. We can barely map, moving toward destinations we cannot see. This raises profound philosophical questions. If Earth's position in space is never repeated, if we're always moving away from every past coordinate, what does that mean for memory? For history, every significant event in your life, your birth, your first words, your first love, occurred at a galactic coordinate that no longer exists in your reference frame. You've traveled tens of billions of kilometers since those moments. In a very real sense, the past doesn't just recede in time, it recedes in space as well. Ancient cultures often spoke of existence as a journey. Aboriginal Australians describe songlines paths across the landscape that trace the movements of creator beings during the dream time. These songs serve as maps, memory aids, and spiritual connections. The land isn't static, it's a record of movement. Hindu cosmology describes the universe as arising from Brahman through a process called Srishti, evolving through cycles, and eventually dissolving back, only to emerge again. The universe breathes expansion and contraction motion and rest. This metaphor captures something modern cosmology confirms. The universe is dynamic at every scale, from quantum fluctuations to the clustering of galaxy superclusters. The Maya believed time itself moved in cycles with different eras, baktuns, following prescribed patterns. While we now understand these cycles as calendar mathematics rather than cosmic forces, the underlying intuition that motion and time are inseparable aligns with modern relativity. If we think of the galactic flow as a river, then Earth is a boat on that river, and has been since the solar system formed 4.5 billion years ago. We've traveled roughly 100,000 light-years through the galaxy in that time, passing through different spiral arms, encountering different stellar neighborhoods, exposed to varying cosmic ray intensities. Some scientists speculate that Earth's passage through different galactic environments might influence climate or even evolution. When the solar system passes through dense regions of interstellar matter, more comets might be knocked loose from the Oort cloud, increasing impact rates. When we pass through spiral arms where supernova rates are higher, cosmic ray exposure increases, potentially affecting atmospheric chemistry and cloud formation. These effects, if real, operate on timescales of millions of years. But they suggest that Earth's galactic journey isn't just scenery. It's an environmental factor shaping the planet's history. The James Webb Space Telescope, operating in infrared wavelengths, can peer through the dust of the zone of avoidance, gradually revealing what lies at the heart of the Great Attractor. Early observations suggest massive galaxy clusters, dense concentrations of dark matter, and complex gravitational fields. The full picture remains incomplete, but each observation refines our understanding of where exactly we're being pulled. Some fringe theories propose even more exotic possibilities. What if the Great Attractor itself is being drawn towards something beyond the observable universe? What if there are structures outside our cosmic horizon so distant that their light hasn't reached us yet, but whose gravity influences everything we can see? Mainstream cosmology treats this as speculation at best. The observable universe has a finite size, roughly 46.5 billion light-years, in radius, limited by the speed of light and the age of the universe. Anything beyond that horizon is by definition unobservable and scientifically untestable. But the question remains haunting: if we're being pulled, what's doing the pulling? And if the puller is also being pulled, where does it end? Perhaps it doesn't. Perhaps motion is all the way down turtles upon turtles, galaxies flowing toward structures flowing toward larger structures in an endless hierarchy. Or perhaps there's a final answer, some ultimate density or structure toward which all cosmic motion flows. We don't know. What we do know is that every point in the universe is moving relative to every other point. There is no cosmic center, no place of absolute rest. Motion is fundamental, not incidental. This has existential implications. If you want to return to a place, you must account not just for Earth's rotation and orbit, but for the Sun's galactic motion and the galaxy's intergalactic motion. In the strictest sense, you can never return anywhere. Every location is temporary, defined only in relation to other moving objects. This is why the ancients were wise to define sacred space, not by coordinates, but by relationships, by alignments, to stars by rivers, and mountains by thresholds between worlds. They understood intuitively that place isn't fixed. It's a moment in a longer journey, a point where paths cross temporarily before continuing onward. As you drift towards sleep tonight, consider this: the pillow beneath your head is moving through the galaxy at 800,000 kilometers per hour. By morning, you'll have traveled 6.4 million kilometers through space, farther than the distance from Earth to the Sun. You'll wake in a place you've never been before, on a planet that has journeyed onward, carried by a sun that orbits a galaxy that flows through space toward a destination none of us will live to see. This is not metaphor. This is literal truth. You are a traveler through the cosmos, whether you chose it or not. The ancient Egyptians spoke of the soul's journey through the afterlife, navigating cosmic rivers guided by stars. Perhaps they understood something we've forgotten, that we're already on that journey, that the cosmos is already carrying us. That motion through space and motion through time are two aspects of the same eternal voyage. Where are we going? Toward the great attractor, toward Shapley, toward structures we cannot yet name. But perhaps the destination matters less than the journey itself, the fact that motion never ceases, that the universe never rests, that we are all always voyaging through the infinite dark. Tomorrow when you wake, remember, you didn't stay here overnight. You passed through, briefly, like all things pass through all places, moving ever onward, never to return. But this galactic journey unfolds on a clock that most people never consult, a clock that ticks slightly faster than the familiar rhythm of days. And that difference, minute as it seems, reshapes the entire calendar of the sky.
Here's a fact that sounds wrong the first time you hear it. A day is not 24 hours long. Earth doesn't need 24 hours to complete one full rotation. It needs 23 hours, 56 minutes, and 4 seconds. Those missing 4 minutes might seem trivial, an astronomer's technical detail irrelevant to daily life. But those 4 minutes are why the stars shift position each night, why the constellations change with the seasons, and why astronomy exists as a science distinct from timekeeping. Let's start with definitions. When astronomers speak of a day, they distinguish between two kinds: the solar day and the sidereal day. A solar day is the interval from one noon to the next, the time it takes for the sun to return to its highest point in the sky. This is the day humans live by, the 24-hour cycle that governs sleep and wakefulness, work and rest. It's defined by Earth's rotation relative to the sun. A sidereal day, by contrast, measures Earth's rotation relative to the distant stars. It's the time required for Earth to spin exactly 360 degrees, returning the same stars to the same position overhead.
This period is 23 hours 56 minutes and 4 seconds 3 minutes and 56 seconds shorter than a solar day. Why the difference? The answer lies in Earth's simultaneous motions. While Earth spins on its axis, it's also orbiting the Sun. Each day, Earth travels about 2.6 million kilometers along its orbital path, roughly 1 degree of its 360-degree annual orbit. When Earth completes one full 360-degree rotation relative to the stars, the Sun appears in a slightly different position because we've moved along our orbit. To bring the same location back in line with the Sun to return to solar noon, Earth must rotate a little bit more, roughly 1 degree extra. That additional rotation takes about 4 minutes. So the solar day is longer because it includes not just Earth's rotation, but a small correction for Earth's orbital motion. This has profound consequences for how we experience the sky. If you go outside tonight and note the position of a particular star, then return 24 hours later, one solar day, that star will have shifted westward by about 1 degree. That's because a solar day is slightly longer than Earth's true rotational period. But if you return in exactly 23 hours, 56 minutes and 4 seconds one sidereal day, the star will be in exactly the same position. This is why professional astronomers use sidereal time. It's the true clock of Earth's rotation, undistorted by orbital motion. Over a month, those 4-minute daily differences accumulate to about 2 hours. Over a year, they sum to a full 24 hours. This is why the night sky changes with the seasons. In July, the constellation Scorpius is prominent after sunset. By October, it's setting earlier, replaced by other constellations. By January, it's not visible in the evening sky at all, not because the constellation moved, but because Earth did. We've orbited to a different position in space, facing a different direction, and the stars we see reflect that change. The ancient Greeks understood this distinction, though they lacked modern terminology. They noted that the fixed stars returned to the same position slightly earlier each night relative to the Sun. This regular shift allowed them to create star catalogs, predicting when specific stars would rise or set throughout the year. Hipparchus, one of antiquity's greatest astronomers, used observations spanning centuries to discover axial precession, the slow wobble of Earth's rotational axis. This wobble occurs over a 26,000-year cycle and shifts the position of the celestial poles. To detect it, he compared his observations of stellar positions to those made 150 years earlier by Timocharis and Aristillus. The stars had shifted more than their solar year motion suggested, proof that Earth's axis itself was moving. This discovery required meticulous attention to sidereal time, tracking the true rotations of Earth against the unchanging stars. The Maya achieved similar precision without the Greek theoretical framework. They calculated the synodic period of Venus, the time between successive identical positions of Venus relative to the Sun, as 583.92 days. Modern measurements give 583.924 days. They were accurate to within 1 day in 6,000 years, a precision requiring careful tracking of sidereal positions over multiple generations. How did they do it without telescopes or mechanical clocks? The answer is patience, continuity of observation, and a cultural commitment to astronomical record-keeping that spanned centuries. Each generation refined the measurements of the previous, accumulating data that revealed patterns invisible within a single lifetime. Today, sidereal time governs astronomical observation. Every major telescope and observatory displays local sidereal time (LST) alongside civil time. When an astronomer wants to observe a particular star, they convert its position, expressed as right ascension and declination, celestial coordinates, into LST. This tells them when the object will be highest in the sky and best positioned for observation. The Hubble Space Telescope, orbiting Earth every 97 minutes, uses sidereal calculations to aim its instruments with extraordinary precision. A target must be acquired and tracked as Earth rotates beneath the telescope. Without sidereal time, this would be impossible. The objects would drift out of view as Earth's rotation carried the telescope through space. The James Webb Space Telescope faces an even more complex challenge. Orbiting the Sun at the L2 Lagrange, 1.5 million kilometers from Earth, it must maintain precise orientation relative to both Earth and celestial targets.
Its pointing algorithms incorporate sidereal time orbital mechanics and precession computing, where a distant galaxy will appear in its field of view, accounting for all simultaneous motions. Yet most people will never knowingly use sidereal time. We live by solar time, by alarm clocks and work schedules, lunch breaks and sunset. The clock on your wall tracks the sun, not the stars. This wasn't always true. Before artificial lighting, before cities glowed at night, the stars were visible and familiar. People knew the sky intimately, recognizing constellations as reliably as they recognized neighbors. They noticed the slow westward drift of each constellation, the seasonal changes, the return of familiar patterns. Farmers planted and harvested by lunar phases and stellar positions, not calendars. Navigators crossed oceans by stars using sidereal positions to determine latitude and time. The sky was a clock calendar and compass combined. Polynesian wayfinders navigating thousands of miles of open Pacific Ocean memorized the rising and setting points of dozens of stars throughout the year. They knew which stars appeared, at which sidereal times, during which months, creating a mental map of space and time that allowed them to traverse the world's largest ocean with astonishing accuracy. They understood intuitively what modern astronomy confirms. Sidereal time is the fundamental rhythm and solar time is a useful approximation. But there's another layer to this. Earth's rotation isn't perfectly constant. Tidal friction from the moon gradually slows Earth's spin, lengthening the day by about 1.7 milliseconds per century. Doesn't sound like much, but it accumulates. 400 million years ago, during the Devonian period, a day lasted only about 22 hours. Coral growth rings from that era show daily, monthly, and yearly cycles, revealing approximately 400 days per year instead of 365. Each day was shorter, but the orbital period 1 year remained the same. This gradual deceleration continues today. NASA's Jet Propulsion Laboratory tracks it using Very Long Baseline Interferometry, VLBI, comparing radio signals from distant quasars observed from multiple locations on Earth. By measuring the exact orientation of Earth's axis and its rotational phase, they detect changes of microseconds. To keep our clocks synchronized with Earth's slowing rotation, international timekeepers occasionally insert a leap second into Coordinated Universal Time (UTC). The last leap second occurred on December 31st, 2016, when clocks briefly read 23:59:60 before advancing to 00:00:00. This adjustment prevents civil time from drifting away from solar time. Without leap seconds, the difference between atomic time, which runs perfectly constant, and solar time, which follows Earth's irregular rotation, would gradually grow. Over centuries, noon would occur while the sun was still rising. Some scientists propose abolishing leap seconds, allowing atomic time and solar time to diverge. The difference would be negligible for decades, but eventually it would become significant, perhaps not in our lifetimes, but in those of our descendants. This debate touches on a fundamental question. What should time measure Earth's rotation, which is natural but irregular, or atomic oscillations which are artificial but perfectly constant? Should time reflect the cosmos or human precision? Ancient peoples would have found this debate absurd. Time to them was the turning of Earth beneath the sun and stars. You couldn't separate time from rotation any more than you could separate night from darkness. They were one and the same. But we've built a civilization that demands precision beyond what nature provides. GPS satellites, financial transactions, computer networks all require synchronization to milliseconds or better.
In this world, Earth's irregular rotation is a bug, not a feature. Yet something is lost in this transition. When time becomes an abstract number divorced from celestial motion, we lose our connection to the cosmos. The 4-minute difference between solar and sidereal days becomes trivia rather than wisdom. Astronomy becomes a specialty rather than common knowledge. Perhaps this is inevitable. Modernity requires precision and nature is messy. But perhaps we can hold both, using atomic clocks for technology while remembering that true time, the time the universe keeps, is measured by rotation under distant stars. Tonight, when the stars come out, try this. Pick one bright star and note its position relative to a landmark, a tree, a building, a mountain. Tomorrow night, return to the same spot at the same clock time. The star will have shifted westward by about 1 degree, roughly 2 moon widths. That's the 4-minute difference made visible. Do this for a week, a month.
Watch the constellations parade westward, rising earlier each night by sidereal time, appearing later by solar time. You're witnessing Earth's orbit made manifest, the planet's journey around the sun written in the shifting sky. The ancient astronomers saw this and built it into stone. Their monuments tracked not just solar events, but stellar ones. The heliacal rising of Sirius, the setting of the Pleiades, the meridian transit of specific stars. They knew that solar time was for living, but sidereal time was for understanding. As you close your eyes tonight, Earth continues its 23-hour, 56-minute and 4-second rotation. The stars wheel overhead, indifferent to human clocks. And tomorrow, when you wake, those stars will have completed one full circuit, one true day, while your clock shows only 23 hours and 56 minutes have passed. The difference is small, but small differences accumulated over time reshape everything.
And nowhere is this more evident than in the single number that determines whether Earth is habitable at all. There's a number that determines whether Earth can support life, 23.4. That's the angle in degrees between Earth's rotational axis and the perpendicular to its orbital plane. It's called the axial tilt, or obliquity. And it's the reason you experience summer and winter, the reason the Arctic has midnight sun, the reason crops grow and migrate with the seasons. Without this tilt, Earth would be a frozen wasteland at the poles, a scorched desert at the equator, and barely habitable in between. There would be no seasons, no variation, no rhythm. Life as we know it would not exist. The concept is geometrically simple. Imagine Earth spinning on an axis like a top. If that axis pointed straight up and down relative to the plane of Earth's orbit around the sun, sunlight would always strike the equator most directly, and the poles would receive barely any light at all. The sun would trace the same path across the sky every single day forever. But Earth's axis doesn't point straight up. It leans to the side by 23.4 degrees. As Earth orbits the sun, this tilt means the northern hemisphere leans toward the sun for half the year and away from it for the other half. The same happens in reverse for the southern hemisphere. When the northern hemisphere tilts toward the sun around June 21st, the summer solstice sunlight strikes it more directly, concentrating solar energy onto a smaller surface area. Days are longer. Temperatures rise. Summer. 6 months later, around December 21st, the northern hemisphere tilts away. Sunlight arrives at a shallow angle, spreading the same energy across a larger area. Days are short. Temperatures drop. Winter. This happens not because Earth is closer to or farther from the sun. In fact, Earth is closest to the sun perihelion during the northern hemisphere's winter, but because of the angle at which sunlight strikes the surface. The ancient Greek geographer Eratosthenes understood this. Around 240 BCE, he famously calculated Earth's circumference using the different angles of sunlight at noon in Alexandria and Siene, modern Aswan. He recognized that the sun's angle varied with latitude, and he used geometry to deduce Earth's size with remarkable accuracy, about 40,000 kilometers, within 2% of modern measurements. But the tilt does more than create seasons. It defines the boundaries of climate zones. At 23.4 degrees north latitude, the Tropic of Cancer marks the northernmost point where the sun can appear directly overhead. At 23.4 degrees south, the Tropic of Capricorn does the same. Between these tropics, the sun passes overhead, at least once per year. Outside them, never. At 66.5 degrees north, 90-23.4, the Arctic Circle marks the latitude where, on the summer solstice, the sun doesn't set. For 24 hours, it circles the horizon. On the winter solstice, it doesn't rise. The Antarctic Circle at 66.5 degrees south marks the same boundary in the southern hemisphere. These aren't arbitrary lines. They're direct consequences of the 23.4-degree tilt geometric truths carved by Earth's orientation in space. The tilt also governs the jet streams, the high-altitude winds that circle the planet and steer weather systems. Uneven heating between equator and poles creates temperature gradients, and Earth's rotation deflects these flows, the Coriolis effect, creating the looping jet streams that dominate mid-latitude weather. Without the tilt, heating would be more uniform. Weather patterns would be simpler, more static. The dynamic climate that allows diverse ecosystems, tropical rainforests, temperate deciduous forests, boreal conifers, Arctic tundra, depends on the tilt creating zones of varying sunlight. But here's the remarkable part. Earth's tilt isn't fixed. It oscillates. Over a period of about 41,000 years, the tilt varies between 22.1 and 24.5 degrees. Currently, it's decreasing, moving toward 22.1 over the next several thousand years. This variation is caused by gravitational interactions with the Moon and other planets, primarily Jupiter and Saturn, which exert slight torques on Earth's equatorial bulge, causing the rotational axis to wobble. This slow oscillation, part of what are called Milankovitch cycles, has profound effects on climate. When the tilt is greater, seasons are more extreme: hotter summers, colder winters, stronger temperature contrasts between equator and poles. When the tilt is smaller, seasons are milder, and ice sheets can grow at high latitudes because summers aren't warm enough to melt winter snow. These cycles are believed to pace the ice ages. Earth has experienced dozens of glacial and interglacial periods over the past 2 million years, with ice sheets advancing and retreating in rough accordance with Milankovitch cycles. The last glacial maximum occurred about 20,000 years ago, when ice sheets covered much of North America and Europe. We're currently in an interglacial period called the Holocene, which began about 11,700 years ago. Geological evidence supports this connection. Ice cores drilled from Greenland and Antarctica contain trapped air bubbles preserving ancient atmospheres. By analyzing oxygen isotopes in the ice, scientists reconstruct past temperatures. The data show clear patterns matching the periodicities of Earth's orbital variations. The 41,000-year tilt cycle, a 26,000-year precession cycle, and cycles in the eccentricity of Earth's orbit. Serbian astrophysicist Milutin Milankovitch proposed this theory in the 1920s, but it wasn't confirmed until the 1970s, when ocean sediment cores provided additional evidence. Milankovitch couldn't have known about plate tectonics, ice cores, or computer climate models. Yet his mathematical astronomy correctly predicted the pacing of ice ages. This demonstrates something profound. Earth's climate is intimately connected to its motion through space. The angle of tilt, the shape of the orbit, the direction the axis points, all of these astronomical variables feed into the climate system, modulating solar input and steering the planet between glacial and interglacial states. But there's an even more critical factor: the Moon. Computer simulations show that without the Moon's stabilizing gravitational influence, Earth's axial tilt would vary chaotically, potentially swinging anywhere from 0 to 85 degrees over periods of millions of years. Imagine a planet where every few million years the poles melt completely, or the equator freezes, or the tilt flips so that one pole points nearly at the sun. Such a planet would experience catastrophic climate instability. Life might never gain a foothold or might be repeatedly extinguished by extreme swings. Complex multicellular life, which took billions of years to evolve on Earth, might never arise. The Moon prevents this. Its gravitational pull exerts a torque on Earth, resisting changes to the tilt angle. As a result, Earth's obliquity varies only between 22.1 and 24.5 degrees over the 41,000-year cycle, a relatively narrow range that keeps climate within survivable bounds. This is one of the many ways the Moon makes Earth habitable. It stabilizes the tilt.
It drives tides which stir the oceans and may have played a role in the origin of life. It even slows Earth's rotation through tidal friction, lengthening the day and transferring angular momentum to the Moon, causing it to slowly recede from Earth at about 3.8 centimeters per year. When the Moon formed, likely from debris ejected when a Mars-sized body called Theia collided with the young Earth about 4.5 billion years ago, it was much closer, orbiting at perhaps 15,000 kilometers instead of today's 384,000 kilometers. Tides were enormous. Days were only 6 hours long, and Earth's obliquity was probably different, though models disagree on whether it was larger or smaller. Over billions of years, the Moon drifted outward, days lengthened, and the tilt stabilized into the gentle oscillation we experience now. This long-term evolution shaped the planet's habitability, perhaps making Earth uniquely suited for life in our solar system. Compare this to Mars.
Mars has a tilt of 25 degrees, similar to Earth's, but no large moon. Its tilt varies chaotically between 13 and 40 degrees over timescales of hundreds of thousands to millions of years. During high tilt periods, Mars's poles may warm significantly, releasing frozen carbon dioxide and water, thickening the atmosphere temporarily. During low tilt periods, the atmosphere freezes out at the poles, thinning to near vacuum. This instability may explain why Mars appears to have had liquid water on its surface billions of years ago but is now a frozen desert. Without a stabilizing moon, its climate swung wildly, making sustained habitability impossible. Venus, rotating slowly and nearly upside down with a tilt of 127 degrees, has no significant tilt variation because it has no large moon and rotates too slowly for tidal effects to matter. But its extreme greenhouse effect and retrograde rotation make it inhospitable for entirely different reasons. Jupiter, massive and distant, also plays a role in Earth's stability. Its gravity nudges smaller bodies like comets either into the inner solar system or out of it. Some scientists argue that Jupiter acts as a shield, reducing impact rates on Earth by gravitationally capturing or ejecting potential impactors. Others suggest Jupiter might occasionally increase impact rates by perturbing objects into Earth-crossing orbits. Either way, the architecture of the solar system, particularly the presence of the Moon and the positioning of Jupiter, appears to contribute to Earth's long-term habitability. This raises a philosophical question. Is Earth lucky, or is the universe filled with similar accidents? The anthropic principle suggests that we shouldn't be surprised to find ourselves on a planet with conditions suitable for life because we couldn't exist elsewhere to observe those conditions. It's a selection effect. We can only observe the kinds of planets capable of producing observers. But this doesn't tell us whether such planets are common or rare. NASA's Kepler mission has identified thousands of exoplanets, many in their star's habitable zone where liquid water could exist. But having liquid water doesn't guarantee complex life. You also need stable climate, a protective magnetic field, an atmosphere that doesn't escape the right chemistry, and perhaps a stabilizing moon. Each requirement narrows the odds. Earth-like planets may be common. Earth-like systems with all the necessary factors may be rare. Recent observations from the James Webb Space Telescope include studies of exoplanet atmospheres searching for biosignatures, signs of life such as oxygen and methane in combination. So far, no definitive biosignatures have been found, but the search has only begun. If life is found elsewhere, one of the first questions will be, what is that planet's axial tilt, and is it stable? As you lie still tonight, consider that Earth's gentle 23.4-degree tilt is a cosmic gift, a geometric accident that creates the rhythm of seasons, the diversity of climate zones, the stability necessary for life to flourish over billions of years. You owe your existence in part to an angle, a number, a tilt that could have been different but isn't. Ancient peoples didn't know the numerical value, but they understood the principle. They watched the sun's path across the sky shift throughout the year, climbing higher, in summer, lower in winter. They built monuments to mark these extremes. Stonehenge, Newgrange, the sun. Dagger of Chaco Canyon, aligning stones with solstice sunrises or equinox shadows. They were measuring the tilt, encoding it in architecture, celebrating it in ritual. They understood that the sun's changing path governed life, that the tilt was sacred geometry written across the sky. We've quantified it, measured it to decimal places, modeled its variations over millennia, but perhaps we've lost some of the reverence. The tilt isn't just a number, it's the reason the world breathes, the reason ice advances and retreats, the reason forests change color and birds migrate. Tomorrow, when the sun rises at an angle determined by latitude season and that 23.4-degree tilt, remember, you're witnessing one of the universe's most delicate balances, an alignment of physics and geometry that makes everything possible. And if Earth's tilt required the moon's presence to remain stable, then perhaps we should look up at night and acknowledge our silent companion, the gravitational anchor that keeps our world from spinning into chaos. But the story of Earth's motion has another layer, another correction humanity made when the calendar fell out of sync with the sky, a correction so dramatic that days simply vanished from history. On September 2, 1752, people across the British Empire went to bed. When they woke the next morning, the date was September 14th. 11 days had vanished, not lived through, not experienced, but erased from the calendar by decree. The reason humanity's clocks had fallen out of sync with the cosmos, and the only way to fix it was to delete time itself. This strange episode in history reveals how difficult it is to measure something as seemingly simple as a year, the time Earth takes to orbit the sun. The trouble began with Julius Caesar. In 46 BCE, advised by the astronomer Sosigenes of Alexandria, Caesar reformed the chaotic Roman calendar. The Julian calendar assumed a year lasted 365.25 days, 365 days plus one leap day every 4 years to account for the extra quarter day. It was elegant, simple, and almost correct, but not quite. The actual length of a tropical year, the time from one spring equinox to the next, is about 365.254 days. The difference is small, roughly 11 minutes per year. But 11 minutes per year accumulates. After 128 years, the Julian calendar gains 1 full day on the solar year. After 1,000 years, it's ahead by nearly 8 days. By the 16th century, 600 years after Caesar's reform, the calendar was off by about 10 days. This might seem like a minor inconvenience, what's 10 days among centuries, but for medieval Europe, deeply religious and tied to liturgical calendars, it was a crisis. The spring equinox, which should occur around March 21st, was happening on March 11th. Easter, calculated based on the equinox and the lunar calendar, was drifting earlier each century. The calendar no longer matched the heavens. Pope Gregory XIII, troubled by this discrepancy, assembled a commission of astronomers and mathematicians. After years of study, they proposed a solution: skip 10 days to restore the equinox to March 21st and reform the leap year rules to prevent future drift. The new rule was elegant century years, like 1600, 1700, 1800 would not be leap years unless divisible by 400. This meant that 1600 and 2000 were leap years, but 1700, 1800, and 1900 were not. This adjustment brings the average calendar year to 365.425 days, much closer to the true tropical year of 365.24219 days. The error is now only 26 seconds per year, meaning the Gregorian calendar will drift by one day only after about 300 years. In October 1582, Catholic Europe implemented the change. Thursday, October 4th was followed by Friday, October 15th. 10 days simply disappeared. But not everyone agreed. Protestant nations suspicious of papal authority refused to adopt the Gregorian calendar. For nearly 2 centuries, Europe operated on 2 different calendars.
When it was October 15th in Catholic France, it was still October 5th in Protestant England. This created diplomatic and commercial confusion. Travelers crossing borders had to adjust dates. Letters sent from one country to another carried 2 dates. Historical events can be difficult to date precisely because sources disagree on whether they occurred on the Julian or Gregorian calendar. Isaac Newton's birth date, for example, is sometimes given as December 25, 1642 Julian calendar used in England at the time, and sometimes as January 4, 1643 Gregorian calendar used elsewhere. Both are correct, depending on reference frame. Britain and its colonies finally adopted the Gregorian calendar in 1752, 170 years after Catholic Europe. By then, the Julian calendar had drifted an additional day, requiring an 11-day correction instead of 10. Parliament decreed September 2, 1752 would be followed by September 14, 1752.
Legend says riots broke out with mobs chanting, "Give us back our 11 days." Modern historians doubt this actually happened. The myth likely arose from satirical cartoons of the era, but confusion was real. Rents, wages, contracts, everything dated needed adjustment. George Washington's birthday shifted from February 11, 1731 Julian to February 22, 1732 Gregorian. He legally had 2 birthdays. The Russian Empire held out even longer, not adopting the Gregorian calendar until 1918, after the Bolshevik Revolution. By then, the Julian calendar was 13 days behind. The October Revolution, which occurred on October 25, 1917 by the Russian calendar, actually took place on November 7th by the Gregorian calendar, leading to confusion about what to call it. Even today, some Orthodox churches use the Julian calendar for religious holidays, meaning Christmas is celebrated on January 7th Gregorian rather than December 25th. This tangled history reveals a profound truth. Time is harder to measure than it seems. The motion of Earth and Sun, elegant as it is, doesn't divide neatly into human units. Nature doesn't care about our preference for round numbers. The tropical year, 365.284219 days, is an irrational number. In the colloquial sense, it doesn't fit neatly into any whole number system. Any calendar that uses only whole days will eventually drift relative to the seasons unless it includes corrections. The Gregorian calendar's leap year system is such a correction, but it's an approximation, not perfection. The 26-second annual discrepancy still accumulates. In another 3,000 years, humanity will need to skip another day, perhaps declaring that 4909 CE will not be a leap year, despite being divisible by 4 or some similar adjustment. The moon's gradual recession adds another wrinkle. As the moon moves away from Earth, tidal friction slows Earth's rotation, lengthening the day by 1.7 milliseconds per century. Eventually, even our leap year rules will need revision to account for a longer day. This is why modern timekeeping uses leap seconds. Atomic clocks, which measure time by the vibrations of cesium atoms, run with perfect regularity. But Earth's rotation is irregular, affected by tides, earthquakes, shifts in ice and water distribution, and other factors. To keep atomic time, called Coordinated Universal Time, or UTC, synchronized with Earth's rotation, the International Earth Rotation and Reference System Service (IRS) occasionally inserts a leap second. The last occurred on December 31st, 2016, when clocks briefly read 23:59:60 before rolling to 00:00:00. Leap seconds are the modern equivalent of the calendar reforms of 1582 and 1752 adjustments to keep human time aligned with astronomical time. But they're controversial. Computer systems sometimes struggle with leap seconds, leading to software glitches. Some scientists propose abolishing them, allowing atomic time and solar time to gradually diverge. If leap seconds are abandoned, the difference would be imperceptible for decades. But over centuries, noon would drift away from solar noon. Eventually, the sun's highest point might occur at 1:00 p.m., then 2:00 p.m. Seasons would remain aligned, leap years, still correct for Earth's orbit, but the sun's daily position would slowly shift. Would this matter? For most modern purposes, probably not. Atomic clocks govern GPS, telecommunications, and financial markets, all indifferent to the sun's position. But for astronomy, agriculture, and anyone who still looks to the sky, it would be a quiet tragedy, the final severing of human time from celestial time. The ancients wouldn't have understood this debate. To them, time was the sun's motion, the moon's phases, the stars' rotation. You couldn't separate time from the heavens any more than you could separate light from the sun. The Egyptians tracked time by the flooding of the Nile itself, triggered by seasonal rains tied to the solar year. The Maya constructed elaborate calendar systems interlocking solar, lunar, and Venus cycles, and they knew these cycles were imperfect, requiring corrections they built into their long count. The Chinese used both solar and lunar calendars, adding intercalary months when needed to keep seasons aligned. They didn't see this as a flaw, but as the nature of things. Time is complex, and managing it requires continuous adjustment. Perhaps that's the real lesson of the 11 vanished days. Time is not a background against which events occur. Time is a relationship between Earth and sun, moon and stars, human activity and cosmic motion. And relationships require maintenance. The Gregorian reform wasn't a one-time fix. It's a system requiring ongoing attention, leap years, leap seconds, eventual further adjustments. Time is negotiated, not discovered. As you close your eyes tonight, consider that the very date you inhabit the number you'd write on a check. The day you'd mark on a calendar is the result of centuries of argument, compromise, and mathematical approximation. September 14th, 1752 follows September 2nd, not because time itself skipped, but because humans decided to realign their counting with the sun. The days didn't vanish. They were never there, or rather, they existed, but were mislabeled the calendar, having drifted away from reality like a clock slowly losing time. Pope Gregory's reform was an acknowledgement of fallibility. Our systems, our imperfect nature is precise, and sometimes we must jump forward to catch up with truth. Tomorrow, when you check the date, remember those missing 11 days and the thousands of hours of careful observation and mathematical reasoning required to notice they were missing at all. The calendar you trust is a collective human effort spanning millennia, a testament to our stubbornness in tracking the heavens despite their refusal to fit neatly into our preferred units. And just as the calendar had to bend to match the cosmos, so too does our understanding of motion. Because Earth isn't just spinning and orbiting, it's wobbling a slow dance that takes 26,000 years to complete. Stand a spinning top on a table and give it a push. Watch as it spins perfectly upright at first. But then, as friction slows it down, something changes. The axis begins to tilt and wobble, tracing a slow circle in the air. The top is precessing its rotational axis itself, rotating in a second slower motion. Earth does the same thing. While Earth spins once every 23 hours and 56 minutes, its rotational axis also traces a slow circle in space, completing one full wobble every 26,000 years. This is called axial precession, and it has profound effects on climate astronomy and human history. The cause is gravitational. Earth isn't a perfect sphere. It bulges slightly at the equator due to its rotation. The sun and moon exert gravitational pull on the bulge, trying to align Earth's axis with the plane of the solar system. But because Earth is spinning, this torque causes precession rather than a simple tilt. Imagine trying to tilt a spinning bicycle wheel by pushing on its axle. Instead of tilting, the axle swings to the side precesses. The same physics governs Earth, just on a vastly longer timescale. As Earth's axis precesses, the direction it points in space slowly changes. Today, the North Celestial Pole, the point in the sky directly above Earth's North Pole, lies very close to the star Polaris. That's why Polaris is the North Star, appearing almost motionless while all other stars wheel around it. But 4,500 years ago, when the Egyptian pyramids were built, Polaris wasn't the North Star. The celestial pole pointed closer to Thuban in the constellation Draco. The Great Pyramid's descending passage aligns toward the position where Thuban would have been visible from deep within the pyramid, possibly for symbolic or religious reasons. In 12,000 years, the celestial pole will point near Vega, one of the brightest stars in the sky. Vega will become the new North Star, and Polaris will be far from the pole, rising and setting like any other star. This slow shift affects more than just pole stars. It also changes when the equinoxes and solstices occur relative to Earth's position in its orbit. Currently, the northern winter solstice occurs when Earth is near perihelion, its closest point to the Sun. This means northern winters are slightly milder than they would otherwise be, because Earth's faster orbital speed, due to Kepler's laws, shortens winter slightly, and the closer proximity to the Sun provides marginally more heat. But 13,000 years ago, due to precession, the situation was reversed. The northern winter solstice occurred near aphelion, Earth's farthest point from the Sun. Northern winters were slightly colder and longer, and summers were hotter and shorter. This amplified seasonal extremes. These changes are part of the Milankovitch cycles, along with variations in axial tilt and orbital eccentricity. Together, they modulate the amount and distribution of solar energy reaching Earth's surface, pacing the advance and retreat of ice sheets over tens of thousands of years. Geological evidence confirms this. Ice core data from Greenland and Antarctica reveal a pattern of glacial and interglacial periods, matching the periodicities predicted by Milankovitch. The last glacial maximum, about 20,000 years ago, occurred when Earth's orbit was more elliptical. The axial tilt was lower, and precession positioned northern summer at aphelion, meaning cooler northern summers, that allowed ice sheets to persist and grow. The discovery of precession is credited to the Greek astronomer Hipparchus around 130 BCE. He compared his observations of stellar positions to those recorded 150 years earlier and found discrepancies that couldn't be explained by measurement error. The stars had shifted systematically, all in the same direction, proof that Earth's axis was moving. This was an astonishing insight. Detecting a 26,000-year cycle within a human lifetime requires comparing observations across generations and recognizing a pattern nearly invisible within any individual's experience. But here's where the story gets strange. Some ancient monuments seem to show knowledge of precession long before Hipparchus. The Sphinx at Giza, for example, faces due east. It has been suggested by researchers like Robert Bauval and Graham Hancock that the Sphinx, the pyramids, and other structures align with the constellation Leo as it appeared on the horizon at the spring equinox around 10,500 BCE, an era when precession positioned Leo differently than it does today. Similarly, Angkor Wat in Cambodia has astronomical alignments that some argue correspond not to the time of its construction, 12th century CE, but to an earlier epoch around 10,500 BCE when precession positioned the stars differently. Göbekli Tepe in Turkey, one of the oldest known megalithic structures dating to around 9600 BCE, features pillars carved with animals that may represent constellations. Some researchers propose these carvings encode knowledge of precession, depicting the sky as it appeared during different epochs. Mainstream archaeology dismisses these ideas as speculative at best, arguing that the alignments are either coincidental or that researchers are retrofitting modern astronomical knowledge onto ancient structures. The dating evidence they point out doesn't support construction in 10500 BCE, only in much later periods, when precession would position stars differently. Yet the precision of certain alignments remains puzzling. How did cultures without writing, without telescopes, without modern mathematics, achieve astronomical orientations accurate to fractions of a degree? And if they did understand precession, if they tracked the 26,000-year wobble, what would that say about continuity of knowledge across millennia? Perhaps the truth lies somewhere between. Ancient peoples were sophisticated observers of the sky. They noticed patterns we've forgotten, spent lifetimes tracking cycles we barely acknowledge. They didn't need to understand the physics of precession to observe its effects, that the constellations visible at spring equinox slowly shifted over generations, that the pole star changed over centuries. They could have encoded this knowledge in myth and monument-preserving observations, even if the theoretical framework was lost. The Hindu concept of the yuga cycles, for instance, describes vast periods of time corresponding roughly to precessional periods. The Zoroastrian concept of the Great Year of 26,000 years appears in Persian texts. The ancient Egyptians spoke of the return of the phoenix after long cycles. Were these merely symbolic or distorted memories of actual astronomical observation? We may never know. But what's certain is that precession continues indifferent to human understanding. The axis wobbles. The pole star changes. The equinoxes drift backward through the zodiac about 50 arcseconds per year, 1 degree every 72 years, one full constellation every 260 years. This is why astrology speaks of ages, the age of Pisces, the age of Aquarius. These refer to which constellation the sun appears in at the spring equinox, a position that shifts due to precession. We're currently transitioning from Pisces to Aquarius, depending on how you define constellation boundaries, a transition that's inspired everything from hippie anthems to New Age prophecies. Astronomers call this phenomenon the precession of the equinoxes. The ancient term was the Great Year, the time for the celestial sphere to complete one full rotation and return to its starting configuration. But here's a subtle point. Precession doesn't affect the seasons themselves. The summer solstice still occurs when the northern hemisphere tilts most toward the sun.
What changes is when in Earth's orbit this happens, and which constellation the sun appears in front of. This distinction confused ancient astronomers. They knew the stars were shifting, but it took genius to recognize this as motion of Earth's axis rather than motion of the stars themselves. Modern measurements of precession come from very long baseline interferometry, VLBI tracking the positions of distant quasars with extraordinary precision. These observations confirm that the precessional period is currently about 25,772 years, though this too varies slightly over time as gravitational influences from planets change. NASA's Jet Propulsion Laboratory models these motions centuries into the future, calculating where Earth's axis will point for astronomical purposes. The James Webb Space Telescope's observation planning requires accounting for precession, ensuring that targets are correctly positioned despite Earth's slow wobble.
This raises a haunting question. If precession takes 26,000 years to complete one cycle and modern humans have existed for perhaps 300,000 years, then Earth's axis has completed more than 11 full wobbles during human existence. Did any ancient culture track the complete cycle? Did anyone 26,000 years ago look up and see Polaris as the pole star exactly where we see it now? We'll never know. But the thought is humbling that the sky above you tonight is the same sky someone saw 26,000 years ago, before civilization, before agriculture, before writing. The stars have completed one full circuit and returned to their positions as if time itself had looped. The ancient Greeks and Hindus both proposed that time was cyclical rather than linear, that the universe repeated itself in vast cycles. Perhaps they intuited something true on precessional timescales. The sky does repeat. The cosmos has a memory, and that memory is 26,000 years long. As you drift towards sleep tonight, imagine the slow wobble Earth's axis tracing an invisible circle in space, so gradual that 1,000 generations live and die between 1 degree and the next. Your life, your civilization, all of recorded history occupies a tiny arc of that circle, a moment in the great year. And yet the wobble continues patient and eternal, the cosmos keeping time on scales that dwarf human experience. The pole star will change, the equinoxes will drift, the great year will complete and begin again as it has for billions of years and will for billions more. But none of this motion, not the spin, not the orbit, not the precession, would be stable without a companion, a gravitational anchor that has guarded Earth's climate for 4.5 billion years. Look up at the moon tonight. That pale sphere hanging in the darkness is more than a beautiful ornament. It's the reason you're alive. Without the moon, Earth's climate would be chaotic, swinging wildly between extremes. The seasons you experience, regular, predictable, following the same rhythm every year, exist because the moon holds Earth's axis steady. This wasn't always known. The moon was thought to govern tides, inspire poetry, and mark months, but its role in climate stability was discovered only recently through computer simulations. In 1993, French astronomer Jacques Lascar ran models of Earth's axial tilt over millions of years. He found something shocking: remove the moon from the simulation, and Earth's obliquity. Its axial tilt varies chaotically between 0 and 85 degrees over periods of hundreds of thousands to millions of years. Imagine a planet that every few million years flips so that its poles face the sun, or stands upright so seasons vanish entirely, or tips so far that the equator becomes the coldest place and the poles the warmest. Any complex life that evolved during one stable period would be extinguished when the tilt swung to an extreme. The planet would be habitable, then uninhabitable, then habitable again, but never long enough for evolution to produce sophisticated organisms. Earth doesn't suffer this fate because the moon's gravity exerts a stabilizing torque. The moon pulls on Earth's equatorial bulge, resisting changes in the tilt angle. As a result, Earth's obliquity varies only between 22.1 and 24.5 degrees over the 41,000-year Milankovitch cycle, a gentle oscillation compared to what could be. This stability isn't just a nice feature, it's foundational to habitability. Life on Earth has had 3.5 billion years of relatively stable climate conditions to evolve in. The sun has brightened significantly over that time, and continents have drifted, but the basic pattern, seasons, ice ages paced by orbital cycles, a temperature range compatible with liquid water, has persisted. The moon made this possible. Mars offers a cautionary comparison. Mars has 2 tiny moons, Phobos and Deimos, neither massive enough to stabilize its axis. Computer models show that Mars's obliquity has varied between 13 and 40 degrees over the past few million years alone, and may have experienced even wider swings in the distant past. When Mars's tilt is high, the poles warm, releasing frozen carbon dioxide and perhaps water vapor, temporarily thickening the atmosphere. When the tilt drops, the atmosphere freezes out at the poles, leaving the planet with barely any air pressure at all. This chaos may explain why Mars transitioned from a world with rivers and lakes evident from dried channels and sedimentary rocks to the frozen desert it is today. Without a large moon, its climate was never stable long enough for life to gain a foothold, or if it did, never stable long enough for that life to evolve into complexity. Venus, spinning slowly backward with a tilt of 177 degrees, essentially upside down, has no moons at all. Its climate is stable, in one sense uniformly hellish, with surface temperatures hot enough to melt lead, but this stability results from a runaway greenhouse effect, not from fortunate orbital mechanics. Earth, by contrast, occupies a Goldilocks position, tilted enough for seasons but not too much, stable enough for long-term evolution but not static. And the moon is the guardian of that stability. How did we get such a fortuitous companion? The leading theory is the giant impact hypothesis. About 4.5 billion years ago, shortly after Earth formed, a Mars-sized protoplanet called Theia collided with the young Earth. The impact was catastrophic, vaporizing much of both bodies, ejecting enormous amounts of debris into orbit. This debris gradually coalesced to form the moon.
Computer simulations of this impact match several key observations. The moon's composition is similar to Earth's mantle, the outer layers. Its orbit is nearly circular and aligned with Earth's equator, and it's unusually large relative to Earth, the largest moon-to-planet size ratio of any terrestrial planet in the solar system. This collision was violent beyond comprehension. The energy released would have melted Earth's entire surface, creating a global magma ocean. Yet from this destruction came Earth's protector, a moon massive enough to stabilize the climate for billions of years. The timing matters. Had the impact occurred earlier, before Earth had differentiated into core and mantle, the chemistry might have been different. Had it occurred later, after life had already emerged, life would have been extinguished. But it happened at just the right moment before life began setting the stage for habitability.
Some scientists call this the lunar catastrophe hypothesis. The worst thing that ever happened to Earth was also the best thing that ever happened to Earth. The moon's stabilizing influence extends beyond axial tilt. Its gravitational pull raises tides in Earth's oceans, and these tides dissipate energy through friction. This tidal friction slows Earth's rotation, lengthening the day by about 1.7 milliseconds per century, and transfers angular momentum to the moon, causing it to gradually recede. When the moon formed, it was perhaps only 15,000 to 20,000 kilometers from Earth, compared to today's 384,000 kilometers. Tides were enormous, possibly hundreds of meters high, and days were only about 6 hours long. Over billions of years, the moon has drifted outward and will continue to do so. In the distant future, perhaps a billion years from now, the moon will be too far away to stabilize Earth's axis effectively. At that point, the axial tilt may begin to vary more widely, and Earth's long-term climate stability could end. But this is so far in the future that other factors, the sun's increasing luminosity, changes in Earth's interior heat flow. Possibly even human activity will likely dominate climate by then. For now, and for the foreseeable future, the moon remains our anchor. Ancient peoples recognized the moon's importance, though not through physics. Nearly every culture deified the moon. In Hindu mythology, Chandra is the lunar deity. In Mayan cosmology, Ixchel governs the moon. The ancient Egyptians worshipped Khonsu, the moon god, associating him with time and healing. These weren't arbitrary choices. The moon was the most obvious celestial timekeeper after the sun, dividing time into months, governing tides, illuminating the night. Its phases were predictable, its cycle recognizable across generations. It was natural to see the moon as a guardian, a protector, a stabilizing force. Perhaps they sensed something we've only recently proven: the moon isn't just beautiful or useful. It's necessary. When you see the moon tonight, consider its gift. That silent companion moving slowly across the sky is the reason Earth's seasons follow predictable patterns. It's the reason complex life had time to evolve. It's the reason you exist. Astrophysicists now search for exomoons around exoplanets, looking for similar stabilizing systems elsewhere in the galaxy. A planet in its star's habitable zone might still be uninhabitable if its axial tilt varies wildly. A large moon changes the equation, making long-term stability possible. This suggests that habitable worlds might require not just the right star, the right distance, the right size, but also the right moon. The conditions for life become narrower, more specific, more unlikely. Earth's moon is a cosmic accident formed from catastrophic violence that happened to be exactly what was needed. The odds of such a collision occurring at the right time with the right mass distribution producing a moon of the right size and orbit are vanishingly small. And yet here we are, protected, stabilized, cradled by gravitational forces we didn't understand until the late 20th century. The anthropic principle suggests we shouldn't be surprised we can only observe universes, galaxies, solar systems where conditions permit observers to exist. If Earth lacked a stabilizing moon, we wouldn't be here to notice its absence. But this doesn't diminish the wonder, it intensifies it. Because the fact that you are here means an extraordinary sequence of events unfolded correctly. The right planet formed in the right place, suffered the right collision at the right time, producing the right moon that stabilized the right tilt for the right duration. One variable out of place, a smaller impact, a different angle, a different timing, and Earth might be lifeless, or populated only by simple organisms never evolving beyond bacterial mats, because the climate kept swinging too wildly for complexity to emerge. The moon is a silent guardian, never speaking, never acknowledged by most who see it. But every season you experience, every predictable cycle of weather, every stable year that allowed agriculture to develop and civilization to flourish, all of it depends on the moon's steady pull. As you rest tonight beneath that pale, watchful eye, know that you're witnessing one of the universe's most delicate balances. A world and its moon locked in gravitational embrace, dancing slowly through the void, their partnership enabling something rare and precious, a stable home for life. The ancient priests who worshiped the moon as a deity weren't entirely wrong. If divinity means that which makes existence possible, that which protects and sustains, then yes, the moon is divine. And tomorrow night, when you see it again, perhaps you'll feel different. Not just looking at a rock in space, but acknowledging a companion, a protector. The reason the earth beneath you stays tilted just right season after season, year after year, for 4.5 billion years, and counting. But even with all this motion, the spinning, orbiting, precessing, stabilized by the moon, there's one more scale to consider. The scale of a human lifetime. How far do you actually travel through space simply by existing? You've never been still, not for a single heartbeat, not for a single breath. Even in the deepest sleep, you are traveling through space at nearly 1,000,000 kilometers per hour. And by the end of an average human lifetime, let's say 100 years, you will have journeyed approximately 9 billion kilometers through the galaxy. That's more than 60 times the distance from the Earth to the Sun, farther than any human-made spacecraft will travel in decades. A voyage beyond comprehension completed without moving a muscle.
Let's calculate this journey. Start with Earth's rotation. If you live near the equator, the ground beneath you moves at 1,670 kilometers per hour. Over 24 hours, you travel about 40,000 kilometers Earth's circumference. In 1 year, that's 14.6 million kilometers just from rotation alone. Add Earth's orbit around the Sun. At 107,000 kilometers per hour, Earth travels roughly 940 million kilometers per year, the circumference of its elliptical orbit. Over 100 years, that's 94 billion kilometers. But wait, the Sun itself orbits the galactic center at 792,000 kilometers per hour. In 1 year, the solar system travels about 7 billion kilometers through the Milky Way. Over 100 years, that's 700 billion kilometers. So which number is correct? All of them, depending on your frame of reference. If you measure motion relative to Earth's center, you travel 14.6 million kilometers per year. Relative to the Sun, 40 million. Relative to the galactic center, 7 billion.
There's no single answer because motion is inherently relative. For the purpose of this meditation, let's focus on galactic motion, the largest scale, the one that truly represents how far you journey through the cosmos. In that frame, during 1 century of life, you travel approximately 700 billion kilometers, or about 9 billion kilometers per year. Put differently, every day, simply by existing, you travel about 19 million kilometers through the galaxy. every hour about 800,000 kilometers, every minute more than 13,000 kilometers. In the time it takes you to sleep for 8 hours, tonight, lying perfectly still unaware, dreaming you'll travel 6.4 million kilometers through space. That's more than 8 times the distance from Earth to the Moon. You'll wake up in a place you've never been before, a point in the galaxy that has never existed in your reference frame until that moment. Every morning is arrival, every night departure. You are a perpetual traveler, and yet you feel nothing. No wind, no acceleration, no sense of motion. Why? Because everything moves with you. The air in your bedroom, the pillow beneath your head, the walls of your home, the ground outside, all of it participates in the same motion. You're not moving through space. You're being carried by space, by a planet that is itself carried by a star that spirals through the galaxy. This is the principle of inertial reference frames taken to its cosmic extreme. You cannot detect constant velocity, only changes in velocity. And the galaxy's motion, while immense, is nearly constant. The variations are so gradual, so smooth, that your nervous system registers nothing. Astronauts aboard the International Space Station experience this more dramatically. They orbit Earth at 27,600 kilometers per hour, completing one lap every 90 minutes. Yet they float weightless, serenely calm, because they and their station fall together toward Earth, constantly missing it as their lateral velocity carries them forward. You experience a gentler version. Earth carries you through its orbit. The Sun carries the whole system through the galaxy. The galaxy itself flows through larger structures. At every scale, motion is shared, synchronized, invisible. But here's the profound part. Every memory you have exists at a different galactic coordinate. The place where you took your first steps. You're now billions of kilometers away from that point in space. Your first day of school. Billions more kilometers behind you. Your first love, your greatest achievement, your deepest sorrow, all of them occurred at locations you will never revisit. In the strictest physical sense, you cannot return to the scene of any memory. Those places don't exist anymore in your reference frame. The universe has moved on, carrying you with it. This gives a strange poignancy to nostalgia. We speak of wanting to go back to a time and place. But even if you return to the physical location, the house where you grew up, the school you attended, you're not truly returning. That location, that moment, existed at a point in space that Earth passed through years or decades ago. You're visiting the same terrestrial coordinates, but different cosmic coordinates. The past doesn't just recede in time, it recedes in space. Ancient philosophies intuited this truth. The Greek philosopher Heraclitus said, "No man ever steps in the same river twice, for it's not the same river and he's not the same man." He might have added, "And the river is not in the same place, for the ground beneath it has journeyed billions of kilometers since the first step." Buddhist teachings emphasize impermanence. Anicca, the idea that nothing remains the same from one moment to the next. Modern physics confirms this at the deepest level. Every particle in your body is in motion, every atom vibrates, every electron orbits, and the entire assembly travels through space at speeds that would be terrifying if we could perceive them. You are not a static object. You are a pattern of motion, a temporary arrangement of matter and energy moving through the cosmos. Hindu cosmology speaks of Shiva's cosmic dance, the Nataraja, the dance of creation and destruction. The universe doesn't sit still, it dances, and you dance with it whether you know it or not. The European Space Agency's Gaia mission has mapped the motions of over 1.5 billion stars within our galaxy. Each star has its own velocity, its own trajectory. When astronomers plot these motions, they see streams and rivers of stars flowing through the Milky Way, gravitationally bound but forever moving. Our sun is part of one such stream. We're not alone in our journey. Thousands of neighboring stars share roughly similar velocities, born from the same giant molecular cloud billions of years ago, now slowly drifting apart but still recognizable as siblings. In a few million years, these sibling stars will have scattered throughout the galaxy. Our neighborhood will look completely different. The constellations you see tonight, Orion, the Big Dipper, Cassiopeia, will have changed shape as stars move at different speeds and in different directions. The sky itself is temporary. The patterns we project onto stars are snapshots of a moment in the galaxy's endless motion. This perspective dissolves the illusion of permanence. Nothing stays, nothing repeats. Every moment is unique, unrepeatable, already receding into cosmic distance. And yet, there's something beautiful in this. You are part of the largest migration in existence, the flow of matter and energy through space-time, the great cosmic current that began 13.8 billion years ago with the Big Bang, and continues still. You didn't choose this journey. It chose you by the simple fact of your existence on a planet that moves in a solar system, that orbits in a galaxy, that flows toward unseen destinations. Ancient creation myths often describe existence as emerging from chaos or void, a transition from stillness to motion, from nothing to becoming. Modern cosmology tells a similar story. The universe began as a singularity, then exploded into motion, and that motion has never stopped. Every atom in your body has been on a 13.8 billion year journey, forged in the cores of ancient stars, scattered by supernova, drifting through interstellar space, accreting into the solar nebula, condensing into planets, cycling through geology and biology, and eventually temporarily assembling into the pattern you call yourself. You are cosmically old. The particles that make you are veterans of journeys spanning light years and eons. And they continue moving, carrying you along for a brief 100 years before disassembling and continuing their voyages. Carl Sagan famously said, "We are made of star stuff." But more precisely, we are moving star stuff. We are motion given temporary form. As you lie still tonight, feel this. Feel the planet spinning beneath you. Feel the orbit carrying you around the sun. Feel the galaxy spiraling onward through the dark. You are moving faster than sound, faster than any bird or plane, faster than comprehension. And in the morning, when you wake, you will be somewhere new. Not just a new day, but a new place, millions of kilometers away from where you closed your eyes. Every day is a journey, every year an odyssey. Every lifetime an epic voyage through the cosmos that dwarfs any voyage humans have undertaken deliberately. The ancient Greeks spoke of nostos, the return home after a journey. But in the cosmic sense, there is no nostos. You cannot return. The home you left this morning is billions of kilometers behind you, unreachable part of the past in both time and space. Perhaps this is why humans have always been restless, always seeking, always moving. We're made by motion. We are motion. To be still is to cease existing, because at the atomic level, at the planetary level, at the galactic level, stillness doesn't exist. Tomorrow, when you stand and walk, remember that your footsteps are the smallest component of your motion. The ground beneath you is already carrying you thousands of kilometers per second. You're walking on a vehicle traveling at near light speed through the galaxy. And yet this motion, this incredible velocity, is also the reason you're safe. Because everything moves together. The atmosphere travels with you, providing air. The magnetic field travels with you, deflecting cosmic radiation. The moon travels with you, stabilizing seasons. The sun travels with you, providing warmth and light. You are part of a convoy, a fleet of matter moving through the cosmos in perfect synchronization, creating the conditions for life through shared motion. So rest now, let the planet carry you. In 8 hours, you'll have traveled 6 million kilometers through the galaxy. But you don't need to steer, you don't need to navigate. The cosmos knows the way. It's been on this journey for billions of years, and it will continue for billions more, carrying you safely through the dark. And when you wake tomorrow in that new place, that new point in space-time you've never visited before, you'll open your eyes to the same familiar room, the same familiar sky, proof that motion and stillness are not opposites, but perspectives, that the universe can be both rushing and serene, both voyage and home. We began with a simple question. How does Earth move? The answer we've discovered is layered, complex, and profound. Earth spins at 670 kilometers per hour. It orbits the Sun at 107,000 kilometers per hour. It spirals through the galaxy at 792,000 kilometers per hour. It precesses over 26,000 years. Its tilt oscillates over 41,000 years. Its orbit stretches and compresses over 100,000 year cycles. And through all this motion, you feel nothing, because motion is not something happening to you. Motion is what you are. We've seen how this motion creates the rhythm of days and nights, seasons and years, how ancient civilizations tracked these rhythms with astonishing precision, encoding astronomical knowledge in stone and myth. How modern science has confirmed, refined, and extended this knowledge using satellites, telescopes, and mathematics. We've discovered that time itself is not universal but relative, flowing differently depending on motion and gravity. That calendars have collapsed and been rebuilt to stay synchronized with Earth's orbit. That the moon is not just a companion but a protector, stabilizing Earth's climate for billions of years. And we've realized that every moment of existence is also a moment of travel, that you journey billions of kilometers through space during your lifetime simply by being alive. What does this mean? Perhaps it means that we are not separate from the cosmos, observing it from outside. We are the cosmos observing itself, matter and energy, arranged into patterns capable of reflection, carried through space by forces that shaped galaxies before our sun was born. Carl Sagan wrote, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." He was describing not just our atomic composition, but our motion, the fact that we participate in cosmic flows, that our trajectories through space connect us to everything that moves. Ancient wisdom traditions understood this in different terms. Hindu philosophy speaks of Brahman, the ultimate reality from which all things emerge and to which all things return. In this view, separation is illusion. Everything is one moving through itself, experiencing itself through countless temporary forms. Buddhist teachings emphasize interdependence, that nothing exists in isolation, that all phenomena arise from relationships. Motion embodies this truth. Your motion is defined only in relation to other moving things. There is no absolute motion, no cosmic center, no privileged reference frame. The Maya understood time as cyclical and layered, with multiple calendars running simultaneously. Modern physics confirms a version of this time is local, relative, and multidimensional. Every reference frame has its own time, its own now, all equally valid. These aren't mystical abstractions. They're descriptions of physical reality expressed in different languages. When you realize that you're always moving, never still, never returning to any past coordinate in space, something shifts. Nostalgia becomes impossible in the strictest sense, because the past literally exists behind you in space as well as time. But presence becomes richer because each moment is truly unique, never to recur. When you realize that Earth's tilt is a cosmic accident that makes life possible, gratitude emerges, not directed at any deity necessarily, but at the sheer improbability that led to this, the collision that created the moon, the tilt that remained stable, the orbit that stayed in the habitable zone for billions of years. When you realize that time flows differently depending on motion and gravity, that simultaneity is local, not universal, that the present moment you experience isn't shared across the cosmos, the nature of reality becomes stranger and more wondrous than any fiction. The ancient astronomers who built Stonehenge and Giza, who calculated planetary motions without telescopes, who tracked precession across generations, they were doing sacred work. Not because they worshipped celestial bodies, but because they were mapping humanity's relationship with motion, with time, with the forces that govern existence. We've inherited their work and extended it. We've sent spacecraft to the edges of the solar system mapping motion with extraordinary precision. We've detected gravitational waves, ripples in space-time itself, proving that motion can shake the fabric of the universe. We've observed distant galaxies moving away from us as space itself expands, carrying them beyond the reach of light. But perhaps we've lost something too. We've gained precision and lost wonder. We know Earth's rotation rate to 9 decimal places, but rarely look up to see the stars wheel overhead. We understand the physics of precession, but don't mark the changing pole star. We predict seasons years in advance, but don't celebrate equinoxes as sacred moments when day and night balance. The ancient peoples had it right. In one sense, these motions matter, not just scientifically, but existentially. The spin of Earth creates the rhythm of your life. The orbit of Earth creates your seasons. The tilt creates your climate. The moon creates stability. The galaxy creates your cosmic neighborhood. You are not an isolated consciousness piloting a body through an indifferent universe. You are a pattern of atoms moving with Earth, with the sun, with the galaxy, participating in flows that connect you to everything that exists. This is both humbling and elevating. Humbling because you're infinitesimally small in the cosmic scale, a brief arrangement on a pale blue dot, as Sagan said. Elevating because that pale blue dot is rare, perhaps unique, certainly precious. And you're part of it. You're here now, conscious and aware, during the brief window when Earth is habitable and humans exist to witness it. So what do we do with this knowledge? Maybe we look up more often. Maybe we notice when the moon is full, when the constellations shift, when sunrise changes position through the year. Maybe we acknowledge that we're passengers on a planet that's been journeying for 4.5 billion years and will continue for billions more. Maybe we treat Earth more gently, recognizing that this stability, this perfect tilt, this protective moon, this just right orbit is rare and fragile, that we've been given something extraordinary not through merit but through accident, and that gratitude demands stewardship. Maybe we extend the circle of consideration. If Earth's motion connects us to the cosmos, then we're part of something larger than nations or species. We're part of the flow of matter and energy through space-time, temporary custodians of complexity in a universe that tends toward entropy. Or maybe we simply rest easier, knowing that the forces carrying us have been reliable for billions of years, that the sun will rise tomorrow because Earth keeps spinning, that seasons will continue because the tilt remains stable, that the moon will keep watch silent and faithful, maintaining the climate that makes everything possible. There's comfort in this. You don't have to steer. You don't have to navigate. The planet knows the way. It's been doing this since before life began, spinning and orbiting and spiraling through space with astonishing consistency. All you need to do is be present. Notice. Wonder. Acknowledge the extraordinary gift of existence on a world in motion. As you close your eyes tonight, consider this final thought: Earth has traveled billions of kilometers since you woke this morning. It will travel billions more before you wake again. In every sense that matters, you're on a journey, the longest, strangest journey any human has ever taken. A journey through space at 1,000,000 kilometers per hour. A journey through time as Earth spins beneath stars that shift each night. A journey through generations, inheriting knowledge from ancient astronomers and passing it forward to descendants who will track motions we cannot imagine. You didn't choose this journey. It chose you. By being born on this planet in this era, you became a traveler through the cosmos, whether you wanted it or not. But here's the gift: you can choose how to experience it.
You can live as if the Earth were still treating days and seasons as abstract repetitions. Or you can live awake to the motion, feeling yourself carried through space, marveling that anything so vast could also feel so gentle.
The ancient Egyptians believed the soul's journey continued after death, sailing through cosmic rivers guided by stars. Perhaps they were describing what we all do, always sailing through the cosmos on a planet ship guided by the same forces that guide galaxies. Where are we going? Toward the great attractor, toward structures beyond our seeing, toward a future we cannot predict. But also in a sense nowhere, because in the cosmos there is no absolute destination, only motion relative to other motion. We're already where we need to be here now, turning beneath the sun, spiraling through the galaxy, carried by forces older than time. So rest well. Dream deep. And when you wake tomorrow, remember, you didn't stay here overnight. You passed through briefly, like all things pass through all places. You're 20 million kilometers farther along in your galactic journey than you were when you closed your eyes. The carousel never stops. The voyage continues. And you, conscious aware, briefly assembled from stardust, get to witness it. What a gift. What an extraordinary, improbable, precious gift. Good night, safe travels. And may the motion that carries you through the darkness bring you safely to another dawn.